Gaze into the deepest heart of darkness in our universe, a place where gravity is so immense that not even light can escape its grasp. We call these cosmic monsters black holes, and for all we think we know about them, they remain some of the most mysterious and awe-inspiring objects in existence. What really happens inside these enigmatic voids? What secrets do they hold beyond their event horizons, the point of no return? Even the brightest scientific minds are still grappling with these questions, and the more we learn, the more we realize just how much we still don't understand. Today, we're about to embark on a journey into the unknown as we explore 30 mind-bending mysteries surrounding black holes and singularities, the infinitely dense points believed to lie at their centers. From the bizarre laws of physics that seem to break down within them, to the startling possibility that they might be gateways to other universes or even tunnels through space-time itself, each mystery challenges our very understanding of reality. These aren't just abstract scientific curiosities, they're cosmic puzzles that force us to rethink everything from the nature of time to the fate of matter itself. Think about it. Somewhere out there, hidden in the silent, star-dusted depths of space, there could be answers to questions we haven't even learned how to ask yet. That sense of wonder, that thrilling uncertainty, is what drives scientists and dreamers alike to keep searching, keep questioning, and keep daring to imagine what might lie beyond. So join us as we dive into the enigmatic world of black holes, where science meets mystery and curiosity has no limits. Now, let's begin with a puzzle so profound that it shook the very foundations of physics, a mystery born from the brilliant mind of Stephen Hawking himself. It's known as the information paradox, and it strikes at the heart of a fundamental rule of the universe. That information, the complete specification of every particle's properties, can never be truly destroyed. You can burn a book, but in theory, if you could collect every single ash particle and trace every puff of smoke, you could reconstruct every word. Quantum mechanics insists this is always true. Information is forever. But then, along came the black hole. Hawking made a stunning discovery. Black holes aren't completely black. Due to weird quantum effects happening right at the very edge of the event horizon, they actually emit a faint glow of particles, now called Hawking radiation. This process slowly steals energy from the black hole, causing it to evaporate over astronomical lengths of time until it presumably vanishes entirely. And that's where the paradox kicks in. The Hawking radiation that escapes appears to be completely random, purely thermal noise that carries no information whatsoever about what fell in. So, if a book falls into a black hole, and the black hole later evaporates into a featureless cloud of this radiation, what happened to the information that made up that book? According to Hawking's original idea, it is irretrievably lost, deleted from the universe. This creates a terrifying crisis, a direct contradiction between the smooth, predictable rules of Einstein's general relativity that govern the black hole's gravity and the unwavering law of quantum mechanics that says information cannot be destroyed. For decades, physicists were split into warring camps. One side sided with Hawking, accepting that information truly vanishes, which would mean rewriting the laws of physics. The other side clung to quantum theory, believing the information must be somehow preserved, but with no clear mechanism for how it could possibly escape the black hole's clutches. The debate raged, symbolized by a famous bet Hawking made, which he initially conceded, only for the mystery to deepen further. Modern theories, like the holographic principle, suggest the information isn't lost but might be smeared across the event horizon like a cosmic fingerprint, encoded in 2 dimensions and then slowly radiated back out in a scrambled, complex way. Yet, a definitive answer remains one of the greatest unsolved problems in theoretical physics, a paradox that forces us to question our most basic understanding of reality, information, and the ultimate fate of what falls into the abyss. And this battle between the infinite and the finite leads us to an even more profound mystery, one that lies at the very core of a black hole's being. If the information paradox is about what happens at the surface, the next great enigma is about what waits in the deepest dark. What is the true nature of the singularity? According to Einstein's theory of general relativity, the ultimate fate of all matter that falls past the event horizon is inevitable and horrifying. It is crushed and compressed by the overwhelming force of gravity, squeezed into an infinitely tiny, infinitely dense point. This is the singularity. The equations tell us that here, the curvature of spacetime becomes infinite. The laws of physics as we know them simply cease to function, and the concepts of time and space lose all meaning. It's a mathematical error code in the universe's operating system, a place where our most successful theory of gravity spectacularly breaks down. An infinite anything in physics is almost always a sign that we're missing a crucial piece of the puzzle. This is where the quest for a theory of quantum gravity becomes paramount. Relativity is the law of the very large governing planets, stars, and the fabric of spacetime itself. Quantum mechanics is the law of the very small, describing the bizarre probabilistic world of atoms and particles. They are both incredibly accurate in their own domains, but they are fundamentally incompatible. The singularity is the epicenter of that conflict. To truly understand what happens at the heart of a black hole, we need a theory that can marry these two giants. A theory of quantum gravity that can describe how gravity works at the microscopic quantum level. Candidates for this unified theory, like string theory or loop quantum gravity, suggest that the singularity might not be a point of true infinity. Instead, they propose a kind of quantum bounce or a transition into an entirely new state of matter. Perhaps there is a smallest possible unit of space, a tiny grain or loop, meaning matter can only be compressed so far before something else must happen. It's like trying to divide a meter stick in half forever. Eventually, you hit a fundamental limit, the Planck length, where our classical ideas of distance stop making sense. The singularity might be replaced by an extremely dense, but not infinitely dense, ball of this exotic quantum material. Solving this mystery wouldn't just satisfy scientific curiosity, it would revolutionize our entire view of reality. It could provide our first glimpse of the universe before the Big Bang, which many models suggest also began as a singularity. It might reveal if black holes are truly gateways to other universes or dimensions, or if they are cosmic dead ends. The nature of the singularity is the final frontier of fundamental physics, a puzzle that challenges us to look beyond infinity and rewrite the rules of the cosmos. But if the information is somehow preserved and encoded on the event horizon, modern physics has stumbled into a terrifying and seemingly absurd consequence. This is the firewall paradox, and it proposes something shocking. The event horizon, rather than being an invisible, uneventful boundary, might actually be a seething wall of blazing energy that would instantly incinerate any matter daring to cross it. This radical idea emerges directly from the battle to solve the information paradox. If information isn't lost, then the Hawking radiation leaking from the black hole must carry that information away. For this to work, the radiation just outside the horizon has to be deeply entangled with the radiation that left earlier, a complex quantum connection that preserves the data. But here's the devastating catch. For the physics to be consistent for an astronaut falling in, that same radiation must also be entangled with the partners of the particles that fell into the black hole long ago. You simply cannot have it both ways. A principle called monogamy of entanglement states that a particle cannot be fully entangled with two different systems at the same time. To save the law of information conservation, something has to give. That something is the peaceful nature of the event horizon itself. The proposed resolution is that all those delicate quantum entanglements must violently break right at the point of the horizon. This sudden severing of countless quantum connections would release an unimaginable amount of energy, creating a literal firewall, a lethal barrier of high-energy particles. This creates an enormous dilemma for physics. Einstein's equivalence principle, a cornerstone of general relativity, assures us that falling through the event horizon of a sufficiently large black hole should be an uneventful, even tranquil experience. You wouldn't feel a sudden jolt or a dramatic boundary. Space-time would simply flow smoothly inward. The firewall hypothesis completely shatters this principle. It suggests that the event horizon is not smooth space but the most violent place in the entire universe. So we are left with a troubling choice. Either we accept that information is destroyed, violating quantum mechanics, or we accept that a firewall exists, violating general relativity. Both options force us to abandon one of our most successful and well-tested theories of physics. The debate is far from settled. Some physicists argue the firewall is a sign that we are profoundly misunderstanding the nature of entanglement or the geometry of space-time near the horizon. Others see it as a crucial clue, pointing toward a new, deeper theory where quantum mechanics and gravity are seamlessly woven together. The firewall paradox isn't just an abstract mathematical argument. It's a stark reminder that when we push our understanding of the universe to its absolute limits, we are forced to confront realities that seem, from our current perspective, completely paradoxical. Yet if the laws of physics allow for a bottomless pit that only consumes, could they also permit its opposite, a cosmic fountain that only gives? This brings us to one of the most fantastical ideas in all of theoretical cosmology, the white hole. In the simplest terms, a white hole is exactly what it sounds like: a black hole running in reverse. Where a black hole's event horizon is a one-way street into oblivion, a white hole's horizon would be a strict exit door. Nothing could ever enter. Matter and energy could only explode outward, erupting from a singularity into the universe. It's a breathtaking concept, but is it anything more than a mathematical fantasy? The idea emerges directly from Einstein's equations of general relativity. These equations are time-symmetric, meaning if you mathematically reverse the direction of time, a valid solution for a black hole transforms into a valid solution for a white hole. They are, in a sense, mirror images of each other within the math. But just because something is mathematically possible does not mean it is physically probable. The second law of thermodynamics, which dictates that entropy or disorder always increases, seems to stand firmly in the way. A white hole suddenly appearing and spewing out ordered energy looks suspiciously like a system that is decreasing entropy, which would violate this fundamental cosmic rule. For many physicists, this is enough to relegate white holes to the realm of mathematical curiosities, elegant ideas that are forbidden from actually forming in our universe. However, some intriguing theories give white holes a potential foothold in reality. One compelling hypothesis connects them directly to the fate of black holes. If a black hole evaporates completely via Hawking radiation, what remains? Does it just wink out of existence? Some models in loop quantum gravity suggest that the immense gravitational collapse that forms a black hole might eventually rebound, like a ball compressed to its limit and then bouncing back. In this scenario, the black hole's singularity would not be a dead end but a transition point, transforming the entire black hole into a white hole, explosively releasing all the matter and energy it had consumed over eons. This process would take an unimaginably long time, far longer than the current age of our universe, meaning any primordial black holes formed at the dawn of time would only now be starting to undergo this spectacular transformation. Perhaps the most profound and captivating possibility is that our entire universe began as a white hole. The Big Bang itself, a singularity from which all matter, energy, space, and time erupted, bears a striking resemblance to a white hole event. We are not falling into it, we are the material that was spewed out. In this view, our universe might be the interior of a white hole that formed from a black hole in another parent universe. This idea offers a tantalizingly elegant and cyclical vision of cosmic evolution, where black holes in one cosmos give birth to new universes through white holes, creating a vast, branching multiverse. While this remains a highly speculative and untested idea, it demonstrates the incredible power of these concepts to challenge our understanding of existence itself, blurring the lines between the beginning of our universe and the ultimate fate of a star collapsed into darkness. This bizarre connection between a black hole's size and its hidden information content led to a revolutionary, almost unbelievable idea about the nature of reality itself. It's called the holographic principle, and it proposes something that sounds like pure science fiction. All the information needed to describe everything within a three-dimensional volume of space. Every star, every planet, every person might actually be encoded on its two-dimensional boundary, like a cosmic projector screen. The story of this astonishing concept begins with entropy. In the 1970s, a young physicist named Jacob Bekenstein made a bold and highly controversial proposal. He argued that a black hole must have entropy. This was a shocking claim because entropy is a measure of disorder or hidden information within a system, and a black hole was supposed to be the simplest object in the universe, defined only by its mass, spin, and charge. According to the famous no-hair theorem, it shouldn't have any messy, complicated internal details. It should be the ultimate ordered system with incredibly low entropy. But Bekenstein realized that when you throw something high in entropy, like a box of gas, into a black hole, that entropy vanishes from our universe. This seemed to violate the second law of thermodynamics, which states that the total entropy of the universe must always increase. His brilliant solution was to propose that the black hole's entropy isn't inside it. It's proportional to the surface area of its event horizon. The horizon itself must record the information about everything that has ever fallen in. Stephen Hawking initially disliked this idea, but his own work on Hawking radiation later confirmed it, and he even calculated the exact formula for a black hole's entropy. This was the first hint that the universe might be playing a profound trick on us. The amount of information a region of space can contain is not determined by its volume, as we would naturally assume, but by its surface area. Think of it this way: if you have an empty sphere, you would expect the maximum number of bits of information you could pack inside it to grow with the cube of its radius, bigger volume, more room for stuff. But the black hole entropy formula tells us it only grows with the square of the radius, just like the surface area. It's as if the entire three-dimensional interior is somehow painted onto the two-dimensional surface. This led physicists like Gerard T. Hooft and Leonard Susskind to propose the holographic principle. In their view, the three-dimensional universe we appear to live in is a holographic projection of information stored on a distant two-dimensional surface. The event horizon of a black hole is a perfect example of such a surface, but the principle might apply to the entire universe. Our perception of depth, solidity, and volume could be an incredibly convincing illusion, much like a three-dimensional image emerging from a flat holographic film. The implications of this are nothing short of earth-shattering for our understanding of reality. It suggests that the fundamental building blocks of space-time and matter are not located within the universe but on its boundary. What we experience as laws of physics playing out in three dimensions could be a direct consequence of how information is processed and translated from that two-dimensional surface. This principle has become a cornerstone of modern attempts to understand quantum gravity, most notably in the study of the AD/CFT correspondence, a specific realization of holography which shows that a gravitational theory in a warped anti-de Sitter space is completely equivalent to a conformal field theory without gravity operating on its boundary. In simpler terms, it provides a dictionary for translating problems in a complex gravitational universe into problems in a simpler, flatland universe without gravity. If true, the holographic principle means we are all, quite literally, living in a shadow play of cosmic proportions, a grand illusion where the true laws of the universe are written on a surface we can never see, forcing us to question the very nature of existence and the meaning of dimensions. Yet if a singularity is nature's ultimate secret, locked away behind the impenetrable curtain of an event horizon, what if that curtain were to fail? This leads us to one of the most unsettling what-ifs in all of theoretical physics, the possibility of a naked singularity. Imagine a point of infinite density where the laws of physics cease to exist, but without the protective shield of a black hole's event horizon. Such an object would be exposed for the entire universe to see, a cosmic sore thumb that would render the very concept of predictability utterly meaningless. The brilliant physicist Roger Penrose found this idea so troubling and disruptive to the foundational principles of science that he proposed a radical solution. He hypothesized that nature itself must possess a kind of built-in modesty, a principle he called cosmic censorship. In simple terms, this conjecture states that every singularity that results from the gravitational collapse of matter must be hidden from view, forever cloaked behind an event horizon. It is nature's way of protecting the universe from the unmitigated chaos that an exposed, naked singularity would unleash. This isn't a proven law of physics, but rather a deeply held belief among many physicists that the universe must, at its core, be predictable. We must be able to use the laws of physics to calculate the future based on the present. A naked singularity would shatter that ability completely. To understand why, consider what happens near a singularity. It is a point where gravity becomes infinite, where space and time are twisted and torn beyond any recognition. Einstein's equations break down, and we simply cannot say what happens next. Inside a black hole, this catastrophic breakdown is contained. It is a private disaster, isolated from the rest of the universe by the event horizon. No signal, no information about the insanity within can ever escape to affect the outside world. The external universe remains safe, predictable, and sane. But a naked singularity would be a public spectacle. Its gravitational field, with its infinite tides, would be on full display. The principle of causality, that cause must come before effect, would be thrown into question. The ability to run the clock forward to make predictions would be impossible because the rules of the game would vanish at the singularity. It would be a gateway to infinite unpredictability, a place where anything could emerge, new universes, impossible objects, or physical laws that change on a whim. The burning question, then, is whether nature actually enforces this censorship. Could a naked singularity ever form? The mathematical solutions within general relativity suggest it might be possible under very specific and extreme conditions. For instance, if a black hole is spinning incredibly fast or possesses a very large electric charge, its internal structure could become so warped that the singularity might not be point-like but shaped like a ring. Some calculations show that if you spin this ring singularity fast enough, the event horizon could theoretically vanish, leaving the ring naked. Other models involving the collapse of exotic forms of matter or in the very early universe also hint at potential loopholes in cosmic censorship. The hunt for these mathematical monsters is more than just an academic exercise. Finding even a theoretical scenario where a naked singularity can form forces us to confront the limits of general relativity and the urgent need for a quantum theory of gravity. It pushes our understanding of the universe to the absolute brink. If a naked singularity were ever observed, it would be the single most important discovery in the history of physics, instantly invalidating Penrose's conjecture and opening a window into the infinite. We would be staring directly into the abyss where physics ends and anything becomes possible. Until then, cosmic censorship remains a foundational, unproven assumption that allows physicists to sleep at night, confident that the universe keeps its most terrifying secrets safely locked away. But if singularities represent the ultimate collapse, how did the universe manage to build such impossibly massive ones so quickly? This brings us to a mystery not of destruction, but of impossibly fast construction: the perplexing origin of supermassive black holes. Nestled at the heart of nearly every large galaxy, including our own Milky Way, these behemoths can weigh in at millions, even billions of times the mass of our Sun. The real head-scratcher isn't just their size, but their age. We have observed fully formed supermassive black holes shining as brilliant quasars from when the universe was less than 1 billion years old, a mere toddler in cosmic terms. How did they gather so much material so fast in such a young and rapidly expanding universe? One leading theory suggests they got a head start, a truly colossal one. This is the direct collapse model. Imagine the early universe not yet filled with the sparkling galaxies we see today, but with vast, pristine clouds of pure hydrogen and helium. Under the right conditions, a particularly massive cloud could have begun to collapse under its own weight. But instead of fragmenting into many smaller clumps that would go on to form clusters of stars, this entire giant cloud, weighing perhaps 100,000 suns or more, would have collapsed directly, in one single cataclysmic event, into a massive black hole seed. This would bypass the long, slow process of stellar evolution entirely, creating a ready-made heavyweight contender from day one. This seed would then have a tremendous gravitational advantage, immediately beginning to voraciously devour the surrounding gas and grow at an astonishing rate. The key ingredient for this scenario is a lack of contaminants. These primordial gas clouds needed to be free of heavier elements, which help gas cool and fragment more easily. It's a compelling idea, but astronomers still debate how common these perfect, pristine conditions actually were. Another, more gradual theory posits that the first generation of stars, known as population 3 stars, were unlike anything we see today. These primordial behemoths, formed from pure hydrogen and helium, could have been incredibly massive, hundreds of times the mass of our Sun. Their immense size would have led to short, violent lives, ending in spectacular supernova that left behind black hole seeds of maybe tens to 100 solar masses. From there, a frantic period of growth would have been necessary. These smaller black holes would have had to merge together through collisions and also accrete surrounding gas at rates that push against the very limits of physics. This process is known as super-Eddington accretion. There's a theoretical speed limit to how quickly a black hole can feed, based on the pressure of the radiation its own meal generates. Too much radiation actually blows the surrounding gas away, shutting off the food supply. To grow as quickly as we observe, these early black holes must have found a way to bypass this limit, perhaps by feasting on dense, chaotic streams of gas in the turbulent environment of the early universe where the radiation could escape through messy, uneven gaps. The puzzle is so profound that it has led to even more exotic proposals. Could some of these supermassive black holes be primordial in nature, formed not from stars or gas clouds at all, but from ultra-dense fluctuations in the very fabric of spacetime in the first moments after the Big Bang? Or is our understanding of accretion physics in those extreme environments simply incomplete? Each of these theories has its own challenges and its own compelling evidence. The direct collapse model provides a massive starting point but requires very specific conditions. The stellar seed model is more common but requires a period of breakneck growth that strains our models. The arrival of powerful new telescopes like the James Webb Space Telescope is poised to shed light on this mystery, peering back to the era of the first galaxies and their central black holes. By census taking counting how many of these giants existed and how big they were at different points in time, we can start to rule out scenarios and piece together the true origin story of the universe's most dominant gravitational engines. Solving this isn't just about explaining black holes, it's about understanding how the largest structures in our universe assembled themselves in the blink of a cosmic eye. While the cosmic stage is dominated by stellar mass black holes and their supermassive cousins, a crucial character in the evolutionary story has been conspicuously absent from the cast: the intermediate mass black hole. Imagine a family tree where you have the children and the grandparents, but you're missing every single parent, aunt, and uncle. That's the perplexing gap in our understanding of how black holes grow. These middleweights are theorized to bridge the vast chasm between the remnants of dead stars, which might be 5 to 100 times the mass of our Sun, and the galactic titans weighing millions or billions of solar masses. The question is, if they are the essential stepping stones, why are they so incredibly difficult to find? The hunt for these missing links focuses on two primary environments: the bustling centers of dense star clusters and the chaotic tails of galaxy collisions. Globular clusters, those ancient spherical swarms of hundreds of thousands of stars tightly bound together, are prime real estate. In such a crowded neighborhood, stellar mass black holes are predicted to sink to the center through dynamical friction, where they could merge with each other or pull in surrounding stars, gradually building up their mass over time. The evidence, however, has been frustratingly indirect. Astronomers don't see the black hole itself. They infer its presence by watching the effect its gravity has on nearby stars. In several clusters, stars have been observed zipping around at incredible speeds near the core, suggesting they are whirling around an invisible, massive anchor. The velocity of these stars points to a gravitational source weighing a few thousand suns, a perfect candidate for an intermediate mass black hole. Yet, alternative explanations persist. This frantic stellar dance could potentially be caused by a dense knot of neutron stars or smaller black holes, making each detection a subject of intense debate rather than a closed case. Another promising hunting ground is within the faint, shimmering glow of dwarf galaxies. These are the small, building block galaxies that are thought to merge to form larger ones like our Milky Way. Many are expected to host their own central black holes, but due to the galaxy's small size, these black holes would be correspondingly smaller, smack in the intermediate mass range. Finding them involves searching for the faint, telltale flicker of accretion or the subtle motions of gas in the galaxy's core. Then there are the extraordinary, fleeting signals from across the cosmos, ultraluminous X-ray sources or ULCs. These are objects that pour out staggering amounts of X-ray radiation, far more than could be explained by a typical stellar mass black hole feeding at its theoretical maximum. One compelling explanation is that we are seeing an intermediate mass black hole in a feeding frenzy, accreting material at a tremendous rate. The most compelling evidence yet came not from light but from ripples in spacetime itself. The LIGO and Virgo gravitational wave observatories have detected mergers between black holes that created final products in the intermediate mass range. Some of the individual black holes that collided were themselves over 50 solar masses, placing them firmly in a mass gap above what we expect from a typical collapsing star, hinting that they might have been the products of previous mergers in dense environments, the very building blocks of these middleweight mysteries. Understanding these elusive objects is about far more than just completing a cosmic checklist. They hold the key to unlocking one of the great riddles of modern astrophysics. How did the supermassive black holes get so big so fast? If the first black holes in the early universe were stellar mass remnants, they would have needed to grow at an almost impossibly rapid rate to become the billion solar mass quasars we observe. Intermediate mass black holes provide a compelling solution. If the early universe was rich with these ready-made middleweights, each one 1,000 or 10,000 times the mass of the Sun, they would have had a colossal head start. They could have served as massive seeds, falling into the centers of nascent galaxies and immediately beginning a rapacious feast on the surrounding gas, quickly snowballing into the supermassive giants we see today. Without confirming their existence and understanding their formation mechanisms, our models of cosmic structure and black hole evolution remain incomplete. missing the vital middle chapter that connects the humble death of a star to the birth of a galactic emperor. Now consider the most violent event since the birth of the universe itself, the moment two black holes, locked in a final gravitational embrace, decide to become one. These collisions are so cataclysmic that they don't just shake the surrounding space, they shake the very fabric of space-time, sending out ripples that travel across the cosmos at the speed of light. For a century, these gravitational waves were merely a prediction of Einstein's theory, an elusive whisper he thought we might never hear. Then, in 2015, the LIGO Observatory did the impossible. It heard the chirp. So what exactly happens when two black holes decide to merge? It's a cosmic dance that unfolds in three devastatingly beautiful acts. First, there's the in-spiral. Two black holes, perhaps born from massive stars that lived and died together as a binary pair, orbit each other for eons, slowly losing energy by radiating gravity waves. This causes their orbits to tighten, drawing them closer and closer together in an ever-quickening spiral. As they near each other, the space-time around them becomes intensely warped, and the waves they emit grow stronger, ringing out across the universe like a siren. Then comes the merger. This is the main event, lasting only a fraction of a second. The two event horizons touch, merge, and violently oscillate, forming a single, highly distorted black hole, often described as being born in chaos. This newborn black hole isn't a smooth sphere, it's a wobbly, lopsided entity, and it must settle down. This is the final act, the ring down. Like a struck bell, the black hole shudders, vibrating and shedding its distortions by emitting a final, powerful burst of gravitational waves until it becomes a perfect, silent sphere. In that brief moment, an amount of energy greater than the combined light of every star in the observable universe is converted into pure space-time vibration. Detecting these faint whispers from billions of light-years away is a triumph of human ingenuity. The LIGO Observatory, with its 4-kilometer-long arms arranged in an L shape, functions as the most precise ruler ever built. A passing gravitational wave literally stretches space in one direction while squeezing it in the perpendicular direction. As the wave passes through the detector, it minutely changes the length of one arm relative to the other by a distance 10,000 times smaller than the nucleus of an atom. To measure this impossibly tiny distortion, scientists fire lasers down both vacuum arms. The light waves travel back and recombine. If the arms are exactly the same length, the light waves cancel each other out. But if a gravitational wave has changed those lengths, the light waves don't cancel perfectly, and that infinitesimal mismatch creates a flicker of light, the signal that tells us a wave has passed. It's like trying to measure a change in the distance to the nearest star that is the width of a human hair. The detection of these waves didn't just confirm Einstein, it opened an entirely new window on the universe, allowing us to hear events we could never hope to see. But for all we've learned, these collisions present profound new mysteries. One of the biggest puzzles is how these black holes get so close in the first place. There are two leading scenarios, and we're still not sure which dominates. In the first, isolated binary evolution, two massive stars are born together, live their lives, and eventually both collapse into black holes. If the supernova explosions that create them aren't too violent to kick them apart, this stellar couple can remain bound, slowly spiraling together over hundreds of millions of years. The second scenario is dynamical formation, which happens in the crowded dance halls of the universe, dense globular clusters or the chaotic centers of galaxies. Here, black holes, as the most massive objects, sink to the center. They interact gravitationally, sometimes forming pairs, and occasionally these pairs get close enough through chaotic interactions to merge. The data from LIGO and Virgo is starting to offer clues, like the spins of the black holes. If their spins are aligned with their orbit, it suggests a quiet, isolated binary life. If their spins are randomly oriented, it points to a chaotic dynamical meeting in a cluster. the answers we're getting so far are a messy mix, suggesting both pathways are at play in our universe. Perhaps the most startling mystery to emerge from these observations is the existence of black holes in what we call the upper mass gap. Based on our models of stellar evolution, we didn't expect to find black holes much larger than about 50 times the mass of our Sun. The physics of how massive stars live and die seems to impose this limit. Yet, LIGO has heard the mergers of black holes weighing 60, 70, even over 90 solar masses. How did they get so big? Were they themselves the products of previous mergers, built up over time in dense stellar environments? Or are our models of the lives of the most massive stars fundamentally incomplete? Each new chirp from the cosmos is a data point, but it's also a question challenging our understanding of star death, binary dynamics, and the growth of black holes across cosmic time. We are not just listening to the echoes of collisions. We are listening to the universe write the rules of its own most extreme physics, and we are only just beginning to understand the language. Yet for all their terrifying power and seemingly eternal nature, even black holes may not last forever. This brings us to one of the most elegant and mind-bending ideas in modern physics, a discovery that forever changed our view of these cosmic vacuums. It's the concept of Hawking radiation, and it suggests that black holes can, in fact, slowly evaporate away, eventually vanishing in a final, spectacular flash of energy. The story of this revelation begins with a profound contradiction. In the early 1970s, a young physicist named Jacob Bekenstein made a radical proposal. He argued that a black hole must have entropy. This was deeply puzzling because entropy is a measure of hidden information, of disorder, and a black hole, according to the no-hair theorem, was supposed to be the simplest object imaginable, defined only by its mass, spin, and charge. It should be the ultimate state of order with incredibly low entropy. Bekenstein's insight was that when you throw something high in entropy, like a box of hot gas, into a black hole, that entropy vanishes from our universe. To rescue the second law of thermodynamics, which states the total entropy of the universe must always increase, he suggested the black hole's entropy wasn't inside it, but was instead proportional to the surface area of its event horizon. The horizon itself must record the information about everything that had ever fallen in. Stephen Hawking initially disliked this idea, thinking Bekenstein had misunderstood his work. But when Hawking set out to prove him wrong, he ended up proving him spectacularly right, and in the process uncovered something even more astonishing. Hawking asked a seemingly simple question: what happens when you apply the bizarre rules of quantum mechanics not to the black hole itself, but to the empty space just outside its event horizon? In quantum theory, empty space is never truly empty. It is a seething, bubbling froth of virtual particles, pairs of particles and antiparticles that constantly pop into existence, borrow energy from the vacuum for an impossibly brief moment, and then almost immediately annihilate each other, returning the energy and vanishing. This isn't just a mathematical quirk. We see the effects of these quantum fluctuations in experiments every day. Now, picture this happening right at the edge of a black hole's event horizon. One of these virtual particle pairs appears. Through a fantastically unlikely but inevitable bit of bad luck, one particle falls across the horizon while its partner escapes into space. The particle that falls in has negative energy, and it effectively reduces the mass of the black hole by a tiny, almost imperceptible amount. The particle that escapes becomes real, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. It's not radiation coming from the black hole itself. It's radiation generated at its expense. From a distance, a black hole would appear to glow with this faint thermal radiation, with a temperature that is inversely proportional to its mass. For a stellar mass black hole, this temperature is a minuscule fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. This means for nearly all black holes in our current era, they are actually absorbing more energy from the space around them than they are losing through Hawking radiation. They are growing, not shrinking, but the universe is expanding and cooling. Billions upon billions of years from now, the background temperature of the cosmos will drop below that of even the largest black holes. At that point, the process of evaporation will finally begin in earnest. As a black hole loses mass, its temperature increases, causing it to radiate away energy even faster. The evaporation accelerates over time in a runaway process, culminating in a final, catastrophic release. In its last second of existence, a black hole would explode with the energy of 1,000,001 megaton hydrogen bombs, vanishing from the universe and leaving behind what? That remains one of the biggest unanswered questions tied to the information paradox. The prospect of ever detecting this faint whisper of radiation from a stellar or supermassive black hole is, with our current technology, virtually impossible. The signal is simply too weak, drowned out by the universe's background noise. However, there is a tantalizing possibility. If much smaller primordial black holes were formed in the intense density of the early universe, some might be reaching the end of their lives right now. Astronomers have searched the sky for the telltale signature of these final explosions. A brief, powerful flash of gamma rays that would stand out from typical supernova or gamma ray bursts. While a few candidates have been proposed, none have been conclusively proven to be a black hole's dying breath. The search continues, as detecting such an event would be a monumental confirmation of Hawking's theory and provide a direct window into quantum gravity. The ultimate fate of black holes, according to this process, is a cold and lonely end. In a far, far future universe that has expanded into darkness, where stars have long since burned out and galaxies have evaporated, the last remaining structures will be these black holes. And one by one, over timescales so vast they dwarf the current age of the universe, they too will glow, heat up, and finally explode into nothingness. The universe would be left a thin, cold soup of fundamental particles and radiation, drifting forever apart in an endless, silent night. Hawking radiation transformed the black hole from a permanent fixture of the cosmos into a transient, albeit incredibly long-lived phenomenon. It connected the world of the immensely large with the world of the incredibly small, offering a profound hint that the key to understanding gravity's ultimate secrets lies in the quantum realm. Faced with this paradox that threatened to unravel physics, theorists embarked on a decades-long quest for a solution, leading to some of the most imaginative and mind-warping ideas in modern science. One of the earliest and most elegant proposals is the concept of black hole complementarity, introduced by Leonard Susskind and others. This principle draws a fascinating parallel to the wave-particle duality in quantum mechanics, where light can behave as both a particle and a wave depending on how you observe it. Complementarity suggests a similar duality for the event horizon. From the perspective of an outside observer watching something fall in, the information is never actually lost. It gets smeared and thermalized across the horizon's surface, encoded in the Hawking radiation that slowly leaks out. But from the perspective of the astronaut bravely falling through the horizon, nothing special happens at that boundary. They continue inward toward their fate, information intact. The radical, almost unbelievable claim of complementarity is that both of these contradictory viewpoints are correct. There is no single objective reality. The information is both reflected at the horizon and passes through it, and the reason this isn't a logical contradiction is because no single observer can ever have access to both truths. An observer outside cannot see inside, and an observer who falls in cannot report back to the outside. It's a cosmic censorship of information itself, preserving the laws of physics by fundamentally limiting perspective. This idea of information being stored on the boundary received a massive boost from string theory, particularly through the work on the anti-de Sitter/conformal field theory, or AD/S/CFT correspondence. This is a concrete realization of the holographic principle, providing a full mathematical dictionary. It states that a gravitational theory describing a black hole in a warped universe is completely equivalent to a non-gravitational quantum theory living on that universe's boundary. In this breathtaking view, the black hole and its interior are a holographic projection. The information about everything that fell in isn't lost inside a pit. It's entirely encoded on the surface, like the data on a Blu-ray disc being projected into a three-dimensional movie. The evaporation process is then just the gradual and complex release of that encoded information back into the universe. The Hawking radiation isn't random thermal noise. It's an intricate, scrambled message containing the history of what was consumed. Decoding that message from the outside is an astronomically complex task, but the information is, in principle, recoverable. The most recent and exciting development in this saga challenges the very premise of the no-hair theorem. For decades, it was a cornerstone of black hole physics, stating that black holes are bald. They can only be described by their mass, electric charge, and spin, with no other distinguishing features or hair. This was the root of the information problem. If two black holes with identical mass, charge, and spin are completely indistinguishable, then all information about what made them is truly gone. However, a team including astrophysicist Andrew Strominger has proposed a revolutionary twist. Black holes might have soft hair. This isn't literal hair, but a term for an infinite number of subtle, quantum-level features imprinted on the event horizon. These features are related to zero-energy particles, or soft particles, that can carry information. The idea is that when something falls into a black hole, it can leave behind an imprint, a subtle displacement in the gravitational field at the horizon. This imprint doesn't require any energy, so it doesn't change the black hole's mass, but it does change its quantum state, providing a way to tag one black hole from another. It's as if every book thrown into the black hole adds a unique, invisible watermark to the edge of the void. This soft hair could provide the missing mechanism for how information is preserved without violating other fundamental principles, offering a potential path to finally resolving the paradox that has haunted physics for half a century. But what if the key to connecting these two worlds isn't a new law, but a hidden bridge in the fabric of spacetime itself? This brings us to one of the most elegant and revolutionary proposals in modern theoretical physics, a concept so profound it feels like it was pulled from the pages of science fiction. It's called the ER=EPR conjecture, and it suggests that the spooky connection of quantum entanglement and the cosmic shortcuts of wormholes might be one and the same thing. To understand this wild idea, we need to unpack its two halves. EPR refers to the famous Einstein-Podolsky-Rosen paradox, the thought experiment that first highlighted the bizarre nature of quantum entanglement. As you might recall, Einstein called it spooky action at a distance. When two particles become entangled, they share a single quantum state. Measure the property of one, say its spin, and you instantly know the property of the other, no matter how far apart they are in the universe. This connection seems to operate faster than light, a notion that deeply troubled Einstein because it appeared to violate the core principles of his own theory of relativity. The other half, ER, stands for Einstein-Rosen. This is a much less famous but equally important piece of work. In 1935, the same year as the EPR paper, Einstein and his colleague Nathan Rosen published a solution to the equations of general relativity that described a bridge connecting two distant points in spacetime. We now call this structure a wormhole. For decades, these two papers were seen as completely separate, even contradictory ideas. One was about the weird, non-local connection of the quantum world, and the other was about the geometry of spacetime in the classical world of gravity. They lived in different universes of thought. The stroke of genius, largely credited to physicists Juan Maldaisner and Leonard Susskind, was to propose that these two concepts are not just similar, they are physically equivalent. ER=EPR. the conjecture boldly states that every pair of entangled particles is, in fact, connected by a microscopic wormhole. That spooky action at a distance isn't magic, it's geometry. The instantaneous connection isn't happening through some mysterious signal. It's because the particles are literally linked by a tiny, subatomic tunnel through the fabric of spacetime itself. The greater the entanglement between two particles, the larger and more robust this Planck-scale wormhole becomes. This idea provides a breathtakingly beautiful potential solution to the black hole information paradox we discussed earlier. Imagine two entangled particles. One falls into a black hole while its partner remains outside. According to the old view, the information carried by the infalling particle is lost behind the event horizon, seemingly forever. But if ER equals EPR is correct, then those two particles aren't just mysteriously linked. They are connected by a microscopic wormhole that bridges the inside and the outside of the black hole. This provides a secret passageway, a back door through which information could, in principle, escape or at least remain connected to the outside universe. The event horizon is no longer a one-way information barrier. It's punctured by a vast network of these tiny wormholes connecting every bit of Hawking radiation to its partner inside. This could explain how information is preserved without violating any laws, neatly sewing up the paradox by weaving gravity and quantum mechanics together with threads of spacetime itself. The implications of this conjecture are staggering. It suggests that the fabric of our universe might be built from a vast, invisible network of entanglement, with every quantum connection literally stitching spacetime together. The geometry of the universe, the very distance between stars and galaxies, could emerge from this cosmic web of quantum links. It turns the universe into a kind of cosmic quantum network, where what we perceive as empty space is actually alive with countless microscopic wormholes, each one a testament to a quantum connection. While this remains a conjecture, a guiding principle rather than a proven theory, it has already revolutionized how physicists think about the deepest questions of reality, offering a tangible bridge between the two greatest theories ever devised and hinting that the universe's most spooky phenomenon might be its most fundamental architectural feature. But if the universe's largest structures are governed by these gravitational titans, could its very fabric be woven from the smallest ones imaginable? This leads us to a hypothesis so elegant it aims to solve two of cosmology's greatest puzzles with a single, breathtaking idea. The mystery of dark matter, that invisible, unidentified substance that makes up over 80% of all matter in the universe, binding galaxies together with its gravitational glue, might find its answer not in a new, exotic particle, but in the oldest objects of all, primordial black holes. The concept is as simple as it is revolutionary. In the incredibly hot, dense soup of the early universe, mere fractions of a second after the Big Bang, random quantum fluctuations in density could have been magnified by the rapid inflationary expansion of space itself. In some regions, this compression could have been so extreme that pockets of matter collapsed directly under their own gravity, bypassing the need to form a star first. These would be primordial black holes, and they could have formed in a staggering range of sizes, from smaller than a single atom to many times the mass of our Sun. Crucially, they would have been forged in the first moment of creation, long before the first stars ever twinkled. If vast numbers of these primordial black holes were created, particularly in a specific mass range, they could be scattered throughout the universe today, completely dark and invisible, yet exerting a powerful gravitational pull on everything around them. They would, in effect, be the dark matter we've been searching for all along. The appeal of this idea is immense. For decades, the leading candidates for dark matter have been hypothetical particles like WIMP, weakly interacting massive particles or actions. Yet, despite enormous, sophisticated experiments designed to detect them, these particles have remained stubbornly elusive. Primordial black holes, on the other hand, require no new physics beyond our well-tested theories of gravity and cosmology. They are a known quantity, just one that formed in an unknown way. This hypothesis offers a beautifully parsimonious solution, using the universe's own established mechanics to account for its most perplexing missing ingredient. Of course, a compelling idea is worthless without evidence, and hunting for these ancient, invisible objects is a formidable challenge. Astronomers have devised several ingenious methods to try and spot them. One of the most successful is gravitational microlensing. The principle is straightforward. If a primordial black hole passes directly between us and a distant star, its gravity will act like a lens, bending the fabric of space-time and focusing the star's light. For a brief period, the star will appear to dramatically brighten before fading back to normal. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, projects like the Optical Gravitational Lensing Experiment, or OGLE, have placed tight constraints on how many primordial black holes of certain masses could be lurking in the galactic halo. So far, these surveys have largely ruled out the possibility that black holes within a wide range of masses, particularly between the mass of a large asteroid and about 100 times the mass of our Sun, could make up all of dark matter. But the hunt is far from over. Other mass windows remain tantalizingly open. At the very low end, black holes with masses similar to a large asteroid could have escaped detection by these microlensing surveys. If they are abundant enough, they could still account for the missing mass. At the other extreme, some models suggest dark matter could be composed of a smaller number of much larger primordial black holes, each one weighing thousands of solar masses. These would be too large and diffuse to create the sharp microlensing signals we look for, but they might reveal themselves through other means, like the subtle gravitational influence they would have on the orbits of stars within a galaxy or the ripples they would create in the delicate distribution of cosmic background radiation. Perhaps the most exciting modern detection method comes from our newfound ability to listen to the cosmos through gravitational waves. The mergers of black holes detected by LIGO and Virgo have provided a census of black hole masses in the universe. Some of these detected black holes fell into a mass range that was somewhat unexpected from standard stellar evolution models, reigniting interest in the possibility that they might be primordial in origin. If a significant population of these ancient black holes exists, future gravitational wave observatories in space will be able to map their distribution and abundance with incredible precision, potentially providing the smoking gun that directly links them to the dark matter halos surrounding galaxies. The case for primordial black holes as dark matter remains unproven, but it is far from closed. It represents a thrilling alternative to the decades-long search for a new particle, a testament to the creative and tenacious spirit of cosmology. Whether this hypothesis ultimately proves correct or not, the search itself is refining our understanding of the early universe and the incredible variety of objects it might have spawned. It forces us to consider that the answer to one of the universe's greatest mysteries might not be a tiny, subtle particle, but a vast population of the most gravitationally powerful objects in existence, hiding in plain sight since the very beginning of time. But if the immense gravity of a black hole defines its outer boundary, its rotation dictates the bizarre and violent physics that plays out just beyond that edge. The spin of a black hole is a property of truly cosmic power, and its primary effect is to twist the very fabric of the universe around it into a swirling vortex. This phenomenon is known as frame dragging, and it represents one of the most dramatic validations of Einstein's theory of general relativity. The theory predicts that any massive rotating object will pull spacetime around with it, like a spinning spoon dragging honey in a circular flow. For a planet like Earth, this effect is minuscule, though we have indeed measured it with incredibly precise gyroscopes on satellites. But for a rapidly spinning black hole, frame dragging is not a subtle curiosity. it is the dominant force that reshapes reality itself. The most stunning consequence of this spacetime whirlpool is the formation of a region outside the event horizon called the ergosphere. Imagine the event horizon as the point of no return, the ultimate boundary. Now picture a larger, flattened sphere like a cosmic pumpkin surrounding that horizon. This is the ergosphere. Within this region, the frame dragging is so ferociously powerful that nothing, absolutely nothing, can remain stationary. The fabric of spacetime itself is being swept around the black hole at such incredible speeds that to resist this flow would require moving faster than light, which is impossible. Every object, every particle, even light itself, is forced to move in the direction of the black hole's rotation, caught in a celestial maelstrom from which there is no escape. It's a place where the very concept of standing still has no meaning, a testament to how rotation can warp the universe in ways that defy our everyday intuition. This relentless, forced motion isn't just a fascinating oddity. It opens the door to what might be the most efficient energy generation process in the entire universe, a concept known as the Penrose process. Imagine an advanced civilization seeking a power source for its galactic empire. They send a mission into the ergosphere of a spinning black hole. There, they deploy a probe that splits into two parts. One part is designed to fall into the black hole, while the other is programmed to escape. The crucial trick is to ensure that the part falling in is given a carefully calculated trajectory so that it enters the black hole with negative energy relative to the outside universe. This isn't science fantasy, it's a direct consequence of the intense frame dragging. Because the infalling piece is stolen by the black hole, the escaping piece is catapulted outward with more energy than the original probe had when it entered. The black hole itself pays the energy bill, its rotational energy slightly decreased by the interaction. In essence, we have a machine that extracts energy from a black hole spin. While this precise scenario is beyond our current technology, the principle is sound, and astrophysicists believe a natural version of this process occurs all the time, potentially powering the incredibly luminous jets that scream from the poles of active supermassive black holes. The mysteries surrounding black hole spin are far from solved. One of the biggest questions is how these cosmic tops get spinning so fast in the first place. A black hole born from the collapse of a single star could inherit a significant spin from its progenitor's rotation. But the supermassive black holes we observe often seem to be rotating at a significant fraction of the maximum speed allowed by physics, a limit where the event horizon itself would begin to break down. How did they achieve such incredible rotational velocities? The answer likely lies in their diet and their history. A black hole that feeds consistently from a single direction, like from a steady accretion disk orbiting in one plane, can act like a child on a merry-go-round, being pushed in the same direction over and over, spinning faster and faster. Conversely, a black hole that receives random, chaotic meals from all directions would have its spin dampened, as impacts from different angles would cancel each other out. Measuring the spin of these giants is an incredibly difficult task, often inferred by studying the X-ray emission from the inner edge of their accretion disks or the shape of the broad ion emission lines that are smeared by the incredible gravitational forces. Each new measurement provides a clue to the black hole's life story, its birth, its growth, and the violent history of its galactic home. The spin of a black hole is more than just a number. It is a dynamic force that sculpts the environment around it, dictating the fate of matter that ventures too close and potentially unlocking energy sources on a scale we can scarcely comprehend. It transforms the black hole from a simple, passive pit into an active, energetic engine at the heart of a galaxy, a whirling dervish that dances to the tune of warped spacetime. And so we arrive at a mystery that seamlessly ties together the threads of entropy, information, and the very laws that govern our cosmos. It's the astonishing revelation that black holes don't just exist within the universe, They actively obey and inform a set of cosmic rules, a kind of thermodynamics for the void. This discovery forged an unbreakable link between the worlds of gravity and heat, concepts that had always seemed utterly distinct, suggesting they are merely different faces of a single, deeper reality. The story of this connection begins with a young physicist named Jacob Bekenstein, who made a proposition that seemed, at the time, almost heretical. He boldly claimed that a black hole must have entropy. This was a shocking idea. In thermodynamics, entropy is a measure of disorder, of hidden information within a system. A messy desk has high entropy, a perfectly arranged, pristine crystal has very low entropy, but a black hole, according to the famous no-hair theorem, was supposed to be the ultimate simple object, the most ordered system imaginable. It could be completely described by just three numbers: its mass, its electric charge, and its spin. It had no other complicated details, no hair. It should have had extremely low entropy. Bekenstein's brilliant insight was realizing that when you throw something high in entropy, like a box of hot, disordered gas, into a black hole, that entropy vanishes from our universe. This act seemed to violate the second law of thermodynamics, which states the total entropy of the universe must always increase. His solution was revolutionary. The entropy isn't destroyed, it is transferred to the black hole itself. He proposed that a black hole's entropy is not inside it, but is instead proportional to the surface area of its event horizon. The horizon itself becomes a ledger, a two-dimensional surface that records the information about everything that has ever fallen in. Initially, this idea was met with deep skepticism, most notably from Stephen Hawking. If a black hole has entropy, Hawking reasoned, then by the standard laws of thermodynamics, it must also have a temperature. And any object with a temperature must emit radiation. But everyone knew the defining feature of a black hole is that nothing, not even light, can escape it. How could it possibly radiate? Hawking set out to prove Bekenstein wrong, but in a stunning turn of events, he ended up proving him right in the most spectacular way possible. By applying quantum mechanics to the space just outside the event horizon, Hawking discovered that black holes do indeed emit radiation. This Hawking radiation, as we now call it, has a perfect thermal spectrum, meaning the black hole has a very real temperature, exactly as the thermodynamic analogy demanded. In that moment, a new field of physics was born, black hole thermodynamics. This led to the formulation of the four laws of black hole mechanics, which mirror the four laws of classical thermodynamics with an almost uncanny precision. The zeroth law states that the surface gravity of a black hole's event horizon is constant, much like temperature is constant throughout a body in thermal equilibrium. The first law relates a change in a black hole's mass to changes in its area, spin, and charge, perfectly echoing the first law's relation between energy, entropy, and work. The second law, now known as the second law of black hole mechanics, states that the total area of all event horizons in the universe can never decrease. This is a direct parallel to the classical second law that entropy always increases. Finally, the third law states that it is impossible to reduce a black hole's surface gravity to zero through any finite process, just as you can never reach absolute zero in a classical system. The profound implication here is that these are not just cute mathematical analogies. Many physicists believe they are literally the same laws. The laws of thermodynamics, which govern the behavior of heat and energy, appear to be a direct consequence of the laws of gravity applied to black holes. This suggests a deep and fundamental connection between information, encoded as entropy on the horizon, and the very fabric of spacetime. The universe seems to be telling us that gravity and thermodynamics are two sides of the same coin, that the flow of heat and the curvature of spacetime are intimately intertwined. This realization has become a guiding light in the quest for a theory of quantum gravity, hinting that the ultimate theory might not be about force and particles, but about information and entropy. It transforms the black hole from a terrifying cosmic vacuum into a Rosetta Stone, a key object for translating between the language of gravity and the language of quantum mechanics, offering us a glimpse into the underlying principles that weave the entire universe together. This elegant but deeply unsettling idea is known as the no-hair theorem, and it suggests that black holes are the universe's ultimate amnesiacs. In the vast and complex cosmos, where every object tells a rich story of its origin and history, a black hole stands apart as a stark, minimalist paradox. According to this theorem, no matter what you throw into a black hole, whether it's a library of every book ever written, a perfect sphere of pure hydrogen, or a chaotic mix of 1,000 different elements, the resulting black hole would be indistinguishable from any other with the same mass, electric charge, and spin. All of the intricate information that defined the original material, its chemical composition, its atomic structure, the specific arrangement of its particles, is completely and irrevocably erased. The black hole retains only three bold numbers: its mass, its charge, and its angular momentum. It has, in the evocative language of physicists, no hair. This theorem emerges directly from the pristine, classical equations of Einstein's general relativity. The solutions to these equations that describe black holes, like the famous Kerr solution for a rotating black hole, are beautifully simple. They possess a kind of mathematical purity governed solely by these three conserved quantities. The profound implication is that black holes are the most featureless objects in existence. They are not just black in color, they are black in information. A black hole formed from the collapse of a single massive star and a black hole formed from the collision of 100 smaller stars would be perfect cosmic twins if their final mass, charge, and spin were identical. This radical simplification poses a terrifying existential question. If information about what falls into a black hole is truly lost forever, what does that mean for our ability to understand the history of the universe? It's as if the cosmos has built-in shredders, capable of destroying the very data that makes reality knowable. But this classical purity immediately crashes into the unyielding rules of the quantum world. Quantum mechanics is built on a foundation of unitarity, the principle that information is never truly destroyed. It can be scrambled, hidden, or transformed into an incredibly complex form, but it must, in principle, always be recoverable. This is the root of the infamous information paradox we explored earlier. The no-hair theorem, in its strictest classical form, seems to demand that information is annihilated, creating a fundamental contradiction that has divided physicists for decades. This clash forces us to ask a critical question: is the no-hair theorem actually correct, or is it merely a simplification that breaks down when we apply a more complete quantum mechanical description of nature? The modern quest to resolve this paradox has led to a dramatic reevaluation of the theorem itself. Many physicists now believe that the no-hair theorem is only approximately true from a distant classical perspective. Up close at the quantum level, the event horizon might be teeming with intricate detail. This is where concepts like the holographic principle and soft hair come into play. The holographic principle suggests that while the three-dimensional interior of the black hole may be bald, all of the information about what fell in is not lost but is instead encoded on its two-dimensional event horizon. The horizon becomes a vast cosmic hard drive, storing a pixelated record of everything it has ever consumed. The information isn't gone, it's just painted onto the surface in a language we are only beginning to decipher. The even more recent idea of soft hair proposes a direct challenge to the theorem's core assertion. It suggests that when particles fall into a black hole, they can leave behind subtle imprints on the gravitational field at the horizon, imprints that don't require energy and thus don't change the black hole's mass, charge, or spin, but do change its quantum mechanical state. These imprints are the soft hair, an infinite number of tiny quantum-level features that could distinguish one black hole from another. In this view, two black holes with identical mass, charge, and spin would not be identical twins after all. They would have different hairstyles, different quantum fingerprints encoding their unique histories. This would provide a mechanism for information to be preserved without violating any other known laws, effectively saving the universe from a profound case of amnesia and potentially sewing up the information paradox by giving black holes a much more complex memory than we ever thought possible. The debate is far from settled, sitting at the white-hot center of theoretical physics. The outcome will determine not just the fate of information in the universe, but the very nature of reality itself. If the no-hair theorem holds in its strictest form, we must be prepared to rewrite quantum mechanics and accept that the universe is fundamentally unpredictable at its core. If, however, quantum effects preserve information through holographic encoding or soft hair, then we are on the cusp of a monumental unification of gravity and quantum mechanics, revealing a cosmos that is infinitely more complex and interconnected than the serene, bald giants of Einstein's equations would have us believe. The black hole's hair, or lack thereof, is now a key to unlocking the deepest secrets of existence. Yet for all their power to consume, black holes are also cosmic engines of creation, capable of firing the most powerful and precise beams of energy in the known universe. These are relativistic jets, and they represent one of the most spectacular and puzzling phenomena in all of astrophysics. Imagine a black hole not as a simple vacuum, but as a celestial cannon. From its poles, it can launch twin beams of superheated plasma, stretching for thousands, even millions of light years across intergalactic space. These jets move at a staggering 99.9% the speed of light, and they carry so much energy that they can outshine the entire galaxy that houses them. The processes that create these beams are so extreme they push the very laws of physics to their absolute limit. The formation of these jets is a complex cosmic ballet, and it begins with the very material the black hole is trying to devour. Most supermassive black holes are surrounded by a vast, swirling disk of gas and dust known as an accretion disk. As this material spirals inward, it is heated to millions of degrees by intense friction and magnetic fields, causing it to glow brilliantly across the electromagnetic spectrum. But not all of this doomed matter actually makes it across the event horizon. The black hole's immense spin and its incredibly powerful magnetic fields, which are frozen into and amplified by the ionized plasma of the disk, work together to create a cosmic escape route. Some of the infalling material, instead of being swallowed, gets funneled and focused by these magnetic field lines toward the black hole's rotational poles. It's as if the chaotic whirlpool of the accretion disk is suddenly given a direction, channeling a fraction of its ferocious energy into two narrow, opposing beams that scream away into the void. The exact mechanism that accelerates the particles within these jets to such phenomenal speeds is the subject of intense study and debate. Magnetic fields are undoubtedly the primary engine. The twisting of these fields due to the black hole's rapid rotation creates a slingshot effect, transferring rotational energy directly to the particles. Think of it like winding up a rubber band tighter and tighter until it finally snaps, releasing all its stored energy at once. In this case, the magnetic field lines act like that rubber band, wound by the black hole's spin, launching particles along them in a process known as the Blandford-Zeenagic mechanism. Within the jets themselves, shock waves likely provide second-stage acceleration. As faster-moving material inside the jet plows into slower-moving material ahead of it, it creates immense shock fronts that act like natural particle accelerators, far more powerful than anything we could ever build on Earth, boosting particles to energies we can barely comprehend. We detect the awesome power of these jets through their spectacular consequences. When a jet is pointed directly at Earth, we see it as a blazar, an object of unbelievable and violent variability, flickering in brightness across all wavelengths in a matter of hours. The high-energy particles within the jets also produce light all across the spectrum, from radio waves to the most energetic gamma rays. Perhaps even more astonishingly, these jets are fundamental architects of their galactic environments. When a jet slams into the tenuous gas that exists between galaxies, it doesn't just quietly stop. It creates massive, balloon-like structures called radio lobes, which can pump enormous energy into the surrounding intergalactic medium. This process can heat the gas, preventing it from cooling and collapsing to form new stars, effectively putting a brake on the growth of the entire galaxy. The supermassive black hole, through its jets, can thus dictate the future evolution of its cosmic home, a testament to the profound interconnectedness between a galaxy and the dark heart that beats within it. This profound and mysterious connection between galaxies and their central black holes is one of the most significant discoveries in modern astronomy. For years, we viewed supermassive black holes as fascinating but largely incidental residents of galactic centers. Then, around the turn of the millennium, astronomers uncovered something astonishing. They found a tight correlation between the mass of a galaxy's central bulge, the dense spherical cluster of stars at its heart, and the mass of its supermassive black hole. The bigger the bulge, the bigger the black hole. This relationship holds true across a staggering range of scales, from small dwarf galaxies to the largest ellipticals, suggesting a fundamental and intimate link between the growth of a galaxy and the growth of the monster at its core. This discovery was as unexpected as it was precise. It's as if the galaxy and the black hole, two structures differing in size by a factor of nearly 1 billion, were somehow communicating with each other, growing in lockstep across cosmic time. The immediate and pressing question became, who is the master and who is the servant? Does the galaxy control the size of its black hole? Or does the black hole somehow dictate the growth and final size of its host galaxy? The answer appears to be a complex and violent cosmic dance, a feedback loop of creation and destruction. The most compelling theory for this co-evolution is known as quasar mode feedback. In the early, gas-rich universe, galaxies are busy forming stars at a ferocious rate. Much of this gas also funnels down to the center, feeding the supermassive black hole and igniting it as a brilliant quasar. For a time, the black hole feasts, but this feast contains the seeds of its own interruption. As the black hole accretes material, it doesn't just quietly consume, it violently gives back. The incredible energy released by the infalling matter in the form of intense radiation and those powerful relativistic jets we discussed generates immense pressure. This energy output can blow away the surrounding reservoir of gas, the very fuel that was feeding both the black hole's growth and the formation of new stars throughout the galaxy. It's a cosmic thermostat. The black hole turns on, gets too loud, and shuts off its own food supply, as well as the galaxy's ability to make new stars. This self-regulating mechanism ensures that the black hole cannot grow indefinitely. Its growth is limited by the size of the galactic bulge it resides in, because a larger bulge can funnel more gas to the center, which in turn allows for a more powerful feedback response that shuts down the process. This elegant loop explains the correlation. The black hole grows until it becomes powerful enough to quench its own growth and that of its host. But this is not the only way black holes leave their mark on galactic evolution. There's another, slower mode of influence known as kinetic mode feedback. In this scenario, which often occurs in older ellipsoidal galaxies, the supermassive black hole is no longer actively feasting as a quasar. Instead, it's relatively quiet but not dormant. It still occasionally accretes matter, and its spin and magnetic fields can launch jets of particles that punch far out into the surrounding intergalactic medium. These jets don't blow away the galaxy's gas, they heat it. By injecting tremendous energy into the halo of hot gas that surrounds many massive galaxies, the black hole prevents this gas from cooling down, falling back into the galaxy, and collapsing to form a new generation of stars. This process is often called maintenance mode or radio mode feedback. It's like a gentle, continuous simmer that keeps the galactic pot from boiling over with star formation. This kinetic feedback is crucial for explaining why the most massive galaxies in the universe are often red and dead, populated with old red stars and showing no signs of the vibrant blue light of newborn stars. The black hole, acting as a central heating system, has effectively put a stop to the galaxy's star-forming career, leaving it to age quietly. The evidence for this incredible partnership is written across the sky. We see it in the correlation between black hole mass and bulge mass. We see it in computer simulations of galaxy formation, which completely fail to produce realistic galaxies unless they include the energetic feedback from a central black hole. Without it, galaxies simply grow too massive and form too many stars, becoming bright blue giants that don't match what we actually observe. We also see it in the fossil records of galaxies themselves. Many galaxies show evidence of past quasar activity, and the most massive ones show signs that their star formation was abruptly quenched long ago, precisely the outcome predicted by these feedback models. This deep, symbiotic relationship forces us to completely revise our picture of galaxies. They are not just islands of stars, they are ecosystems with a supermassive black hole acting as a powerful regulatory heart, pumping energy out into its surroundings and governing the life cycle of the entire structure. The galaxy provides the food, and the black hole provides the discipline, ensuring that growth does not spiral out of control. This cosmic feedback mechanism, playing out over billions of years, is the invisible hand that sculpts the grand architecture of the universe we see today. But to truly grasp the cosmic drama unfolding at the precipice of a black hole, we must venture into the bizarre quantum realm that governs the smallest scales of reality. This brings us to the strange and counterintuitive world of quantum effects near the event horizon, a place where the void itself becomes a seething cauldron of spontaneous creation and destruction. According to the principles of quantum field theory, what we perceive as empty space is anything but. It is a dynamic, boiling sea of virtual particles, fleeting pairs of particles and antiparticles that constantly wink into and out of existence, borrowing energy from the vacuum for a time so brief it defies measurement before annihilating each other and vanishing without a trace. This isn't just theoretical. We see the tangible effects of these quantum fluctuations in experiments like the Casimir effect, where two uncharged metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these virtual particles popping into being on the outside. Now imagine this quantum froth happening right at the very edge of an event horizon. This is where the situation becomes truly dramatic. One of these virtual particle pairs appears. In a breathtakingly rare but statistically inevitable turn of events, the two particles are born precisely on either side of the point of no return. One particle with negative energy falls across the horizon and into the black hole. Its partner, now suddenly real and possessing positive energy, is left stranded outside, free to escape into the universe. This is the fundamental mechanism behind Hawking radiation. But the implications run far deeper than just a slow leak of energy. This process of pair production and separation subjects the very fabric of spacetime to immense stress. The event horizon acts as a cosmic shredder, violently tearing these entangled quantum partners apart. This separation requires energy and exerts a kind of quantum pressure on the horizon itself, a back reaction that could subtly alter the black hole's geometry and potentially even how we define its surface. These relentless quantum fluctuations might do more than just power radiation. They could fundamentally change the nature of the event horizon from a perfectly smooth, classical membrane into a fuzzy, quantum-bathed boundary. Some theories suggest that at the Planck scale, the horizon might not be a sharp line but a blurred and frothy region, more of a transitional zone than a definitive border. This quantum fuzz could potentially resolve some of the paradoxes associated with the horizon, like the firewall, by smearing out the point of infinite drama into a more gradual quantum transition. The energy and information contained within these fluctuations could be the key to understanding how data is transferred from the infalling matter to the outgoing Hawking radiation, providing a possible escape route for information without violating the laws of physics. In this view, the event horizon is not a passive wall but an incredibly dynamic and active interface, where the quantum vacuum itself is being constantly excited and manipulated by the black hole's immense gravity, creating a laboratory for the most extreme physics imaginable and forcing us to reconcile the smooth, geometric world of general relativity with the probabilistic, fluctuating world of the quantum. Yet for centuries, these cosmic leviathans were ghosts in the machine of the universe, their existence inferred only by their gravitational influence on the world around them. That all changed on April 10, 2019, when the Event Horizon Telescope collaboration unveiled an image that stopped the world, the first direct visual evidence of the supermassive black hole at the heart of the galaxy Messier 87. This was not a photograph in the traditional sense, but a monumental reconstruction of data from a virtual telescope the size of Earth itself. But what are we actually looking at in that now iconic image of a fiery, asymmetric ring of light encircling a central region of profound darkness? We are witnessing the black hole's shadow, a silhouette cast against the backdrop of its own immense gravity, and it is one of the most powerful tests of Einstein's theory ever conducted. This central dark region is not the event horizon itself. Instead, it is something larger, a consequence of light's ultimate struggle against gravity. The black hole's incredible mass warps the spacetime around it so severely that it acts like a lens, bending the paths of light rays from the hot, swirling accretion disk behind and around it. Some of this light is bent around the black hole and redirected toward us, creating the bright ring we see. However, light rays that pass too close to the event horizon are not bent, they are captured. They cross the point of no return and are swallowed by the black hole, never to be seen again. This creates a dark absence in the center, a shadow that is roughly 2.5 times wider than the actual event horizon. It is a negative image, a silhouette of the black hole's gravitational grip on the universe, revealing the point where light itself is extinguished. One of the most profound mysteries to emerge from this image is its near-perfect circularity. The black hole in Messier 87 is known to be spinning, and according to our understanding of general relativity, a rapidly rotating black hole should be oblate or flattened due to the frame-dragging effect of its spin. This distortion should in turn warp the shadow it casts, making it appear asymmetrical, more like a crescent or a dented circle. Yet the shadow we observed is stunningly circular. This presents a fascinating puzzle for physicists. It could be that our viewing angle is almost perfectly face-on, looking directly down the black hole's rotational pole, which would minimize the apparent distortion. Alternatively, it might be telling us something new about the dynamics of the accretion flow itself. Perhaps the disk of material is aligned in such a way that it smooths out the shadow's appearance. Or, in the most exciting scenario, this perfect circle could be a subtle hint that our understanding of gravity in these most extreme regimes needs a tiny adjustment. The circular shadow is a powerful confirmation of Einstein's theory in a regime where it had never been directly tested before, but its pristine shape also leaves room for future discoveries that could refine or even extend our models of gravity. The very existence of this shadow is a direct probe of the black hole's most fundamental properties. Its size is dictated by the black hole's mass, providing a direct and independent way to weigh these cosmic giants. Furthermore, the asymmetry in the brightness of the ring, a feature clearly visible in the image, with one side dramatically brighter than the other, is a direct signature of the Doppler effect and relativistic beaming within the swirling accretion disk. The bright side is the part of the disk that is rotating at a significant fraction of light speed toward us. It's light amplified and blue-shifted. The dimmer side is the material whirling away from us. It's light redshifted and dimmed. This lopsided ring of fire is not an imperfection in the image. It is a precise confirmation of the relativistic physics at play, a beautiful and violent dance of matter and light happening just outside the point of oblivion. The black hole's shadow is far more than a picture. It is a complex data-rich message from the edge of space-time, and we are only just beginning to decode its deepest secrets. What exactly happens to a star, a planet, or an unlucky spacecraft after it crosses the event horizon? This is perhaps the most intimate and terrifying of all black hole mysteries, because it asks about the ultimate fate of substance itself. From our perspective outside, the story seems to end at the point of no return. Time slows to a halt for the infalling object from our viewpoint, and it appears to fade from existence, stretched into a thin, red-shifted smear frozen on the horizon for all eternity. But for the object itself, if we could ride along, the journey is just beginning. A one-way trip into a reality where all known physics is turned on its head. According to the pristine equations of Einstein's general relativity, the fate of matter is both simple and horrifying. Once across the horizon, the inward pull of gravity becomes unavoidable. There is no force in the universe that can counteract it. Every possible path for any particle points inexorably toward the center. For a sufficiently large black hole, this journey might initially be uneventful. But as the center draws nearer, the tidal forces become extreme. The difference in gravity between your head and your feet would stretch you into a long, thin strand of atoms in a process picturesquely named spaghettification. Every molecule, every atom, and eventually every fundamental particle would be pulled apart from its neighbors. This stream of particles continues inward, accelerating toward the final destination, the singularity. At that infinitely dense point, the equations blow up. General relativity predicts that the matter is crushed out of existence, its mass, energy, and information simply added to the singularity, making it ever so slightly more massive. In this classical view, matter ceases to be matter. It becomes a featureless part of the black hole's central point mass, losing all identity and structure forever. However, we know that general relativity is an incomplete picture because it ignores quantum mechanics. This is where the fate of matter becomes far more uncertain and fascinating. Quantum theory suggests that information cannot be destroyed. So if the matter is annihilated at the singularity, we have a paradox. Modern theories of quantum gravity propose several alternative, deeply strange destinies. One possibility is that matter never actually reaches a point like singularity. Instead, the extreme conditions might trigger a quantum bounce. In loop quantum gravity, for example, the repulsive force of quantum gravity becomes so powerful at a trillionth of a centimeter that it prevents total collapse. The compressed matter would rebound, potentially exploding outward into a new region of spacetime, perhaps even becoming the seed for a new universe in a white hole transformation. In this scenario, the matter isn't destroyed, it is recycled and repurposed on a cosmic scale. Another mind-bending idea comes from string theory, which suggests that the fundamental constituents of matter, strings and brains, might be reassembled by the black hole. The information that defined the original object could be broken down and then holographically encoded onto the vibrating strings that make up the event horizon's surface. The matter's mass energy would be radiated away over eons as Hawking radiation, but its essential information would be preserved in a scrambled, thermalized form on this two-dimensional surface. From this perspective, matter is not crushed but translated. Its three-dimensional structure meticulously painted onto the boundary of the black hole like a cosmic tattoo. Perhaps the most radical speculation is that the singularity is not an end point at all, but a gateway. The equations allow for the possibility that the singularity bridges our universe to another, either a different region of our own cosmos or an entirely separate universe within a vast multiverse. In this view, the matter that falls in is not destroyed but transported, spewed out through a white hole into a new reality with its own physical laws. While this remains firmly in the realm of theoretical speculation, it highlights the profound truth that at the heart of a black hole, our current understanding of physics reaches its breaking point. The ultimate fate of matter is the ultimate question mark, forcing us to confront the possibility that destruction is an illusion, and that in the universe's most extreme environments, transformation is the only true constant. While we ponder the fate of matter falling into the abyss, its ultimate destruction or transformation, we can't help but wonder if that immense gravitational power could be harnessed for the most fantastic journey of all, a voyage not just through space but through time itself. This brings us to one of the most alluring and mind-bending possibilities in all of theoretical physics, the potential for black holes to act as natural time machines. The foundation for this incredible idea is rooted squarely in Einstein's theory of general relativity, which tells us that gravity doesn't just bend space, it warps time. The stronger the gravitational field, the more time slows down relative to a distant observer. This effect, known as gravitational time dilation, is a proven fact. Our GPS satellites orbiting in Earth's weaker gravity have to have their clocks constantly corrected because they run ever so slightly faster than clocks on the surface. Now amplify that effect to the extreme environment of a black hole. If you could hover just outside the event horizon of a supermassive black hole, where gravity is unimaginably strong but the tidal forces are still survivable, time for you would crawl to a near standstill. From your perspective, a few hours might pass, but when you return to your ship parked at a safe distance, you would find that centuries or even millennia had flown by for the rest of the universe. In this very real sense, you would have traveled into the far future. This isn't science fiction. It's a direct and dramatic consequence of the laws of physics as we understand them. The black hole becomes a time capsule, allowing you to leap forward in time in a single bound. But traveling to the future is one thing, going back is an entirely different and far more problematic proposition. This is where wormholes enter the picture. As we've discussed, certain solutions to Einstein's equations allow for these tunnel shortcuts connecting two distant points in spacetime. If a traversable wormhole could exist, and if one of its mouths could be moved relative to the other, special relativity introduces another form of time dilation. Imagine taking one end of the wormhole and accelerating it to a significant fraction of the speed of light on a long journey, and then bringing it back. Because of time dilation, less time would have passed for the moving end than for the stationary end. The two mouths would now be out of sync, with one existing in the past relative to the other. If you were to then step into the mouth that had stayed behind, you would instantly exit from the moving mouth at a point in time before you even entered. You would have traveled into your own past. However, the obstacles to making this work are not just technological, they are fundamental. The first and most glaring problem is that wormholes, as described by general relativity, are almost certainly not stable. They would require a form of matter with negative energy density, often called exotic matter, to prop them open and prevent the tunnel from collapsing instantly. While quantum mechanics allows for tiny, fleeting amounts of negative energy in certain circumstances, the sheer quantity needed to stabilize a wormhole large enough for a person is almost certainly impossible to obtain. The energy requirements are literally astronomical, and the laws of quantum physics may outright forbid the macroscopic stockpiling of such exotic material. Beyond the immense practical hurdles, we are confronted by the infamous paradoxes that time travel to the past introduces. The grandfather paradox is the most classic example. What happens if you go back in time and prevent your own grandfather from meeting your grandmother, thereby preventing your own birth? This creates a logical inconsistency that seems to violate causality itself. the fundamental principle that cause must precede effect. Physics abhors a paradox, and many theorists believe the universe has built-in mechanisms to prevent such inconsistencies from occurring. Some proposals, like the Novikov self-consistency principle, suggest that any actions taken by a time traveler were always part of history, meaning you could not change the past, only fulfill it. Your attempt to create a paradox would inevitably fail through a seemingly impossible series of coincidences. Other ideas, like the many worlds interpretation of quantum mechanics, propose that traveling to the past would simply spawn a new, parallel timeline, allowing you to change events without affecting your own original history. While this neatly sidesteps the paradox, it means you could never return to the exact universe you left. The tantalizing conclusion is that while the mathematics of general relativity leaves the door to time travel slightly ajar, the laws of quantum physics seem to want to slam it shut. The requirement for exotic matter might be nature's way of imposing a cosmic censorship on causality violation, preventing the past from being altered. For now, black holes remain fantastic machines for hurling us into the future, but the dream of revisiting the past likely remains just that, a dream. Yet, the very fact that our most successful theory of gravity allows us to even entertain these possibilities is a testament to its profound and bizarre beauty, constantly challenging our understanding of reality and our place within the flow of time. Yet, as we contemplate the role of black holes in the life cycle of galaxies, we must also consider their potential impact on the cosmos at its grandest scale. This brings us to a truly profound and revolutionary hypothesis, one that suggests these gravitational behemoths might be linked to the greatest mystery in all of modern cosmology, the accelerating expansion of the universe driven by the elusive force known as dark energy. For decades, astronomers have been grappling with a startling discovery. Not only is the universe expanding, but this expansion is speeding up. Galaxies are flying apart from one another at an ever-increasing rate, a phenomenon that defies the expectation that gravity should be slowing everything down. To explain this, scientists invoke dark energy, a mysterious form of energy inherent to the fabric of space itself, which makes up about 70% of the total energy content of the universe and exerts a kind of negative pressure, pushing the cosmos apart. But what is dark energy? The leading candidate is the cosmological constant, a form of vacuum energy that Einstein originally proposed and then discarded. But there's a massive problem. When physicists try to calculate the expected value of this vacuum energy from quantum field theory, the number they get is wrong by a factor of 10 to the power of 120. This is the largest discrepancy between theory and observation in the entire history of science. This colossal failure has forced physicists to look for alternative explanations, and one of the most daring proposals directly implicates black holes. The idea, put forward by a team including renowned physicist Kevin Croker, is both simple and radical. What if dark energy isn't a property of empty space, but is instead stored within material objects? And what if the prime candidates for storing this energy are the most enigmatic objects we know, black holes? The theory suggests that black holes might contain a form of vacuum energy in their interiors, and that as the universe expands, these black holes grow in mass not only by accreting matter, but also by gaining energy tied to the expansion itself. In this view, the mass of a black hole is not static, it evolves with the cosmic scale factor. As the universe gets bigger, the black holes get more massive, and this growth contributes to the overall energy budget of the cosmos in a way that mimics the effect of dark energy. This concept turns the standard story of black hole formation on its head. Instead of being formed solely by the collapse of stars and subsequent mergers, black holes in this model are intrinsically coupled to the expansion history of the universe. They are not isolated entities, they are integral components of the cosmic fabric, their evolution woven into the very evolution of space-time. This provides a potential solution to the cosmic coincidence problem. Why are the energy densities of dark matter and dark energy roughly comparable today? In this model, it's not a coincidence at all. The growth of black holes, which are linked to dark matter in some formulations, is directly tied to the manifestation of dark energy. The implications of this are staggering. It would mean that the supermassive black holes we observe at the centers of galaxies are not merely byproducts of galaxy formation, they are active drivers of cosmic evolution. Their growth over billions of years would be a key ingredient in the accelerating expansion we measure today. This idea also makes a testable prediction. If black holes are truly coupled to the expansion of the universe and contain this vacuum energy, then their mass should increase in a very specific way over cosmic time. By studying the growth of supermassive black holes across different epochs, comparing their masses in the early universe to their masses now, astronomers could look for evidence of this extra growth that can't be explained by accretion and mergers alone. Recent analyses of populations of black holes have shown some tantalizing hints that they may indeed be growing faster than expected, though the evidence is still far from conclusive. Naturally, this is a highly speculative and controversial idea that challenges many established tenets of astrophysics. Critics point out significant hurdles, such as how this vacuum energy would be physically contained within the black hole without violating other principles. However, its great power is that it offers a potential link between two of the most profound puzzles in the universe, the nature of dark energy and the physics of black holes, suggesting they are not separate mysteries but different expressions of a single, deeper cosmological truth. If confirmed, it would represent a monumental unification of concepts, revealing that the largest and smallest phenomena in the cosmos are fundamentally interconnected, and that the key to understanding the fate of the entire universe might lie hidden behind the event horizons of its most perfect dark objects. But what if the terrifying singularity, that point of infinite density, is nothing more than a mathematical illusion, a sign that Einstein's theory has been pushed beyond its limits and that a deeper truth awaits in the quantum realm? This brings us to a fascinating and hopeful alternative, a concept that aims to tame the infinite and replace the monstrous singularity with a physically plausible object. Enter the Planck star, a theoretical remnant at the heart of a black hole where quantum gravity takes over and performs a miraculous rescue. The problem with the classical singularity is that it represents a complete breakdown of physics. Infinity is not a number we ever measure in nature. It's a signpost that our equations are incomplete. To resolve this, we need a theory of quantum gravity, which seeks to describe how gravity behaves at the unimaginably tiny scale of the Planck length, about 1.6 times 10 to the negative 35 meters. This is the scale where the smooth, continuous fabric of spacetime predicted by general relativity is expected to break down into a discrete, grainy structure, much like a digital pixel or a tiny loop. In this quantum landscape, matter cannot be compressed into an infinitely small point. There is a fundamental limit, a smallest possible volume. When a collapsing star reaches this incredible density, the repulsive force of quantum gravity is theorized to become overwhelmingly powerful, bringing the collapse to an abrupt halt. The result is not a singularity, but an extremely dense ball of matter hovering at the Planck density. This is the Planck star. It would be a sphere with a diameter roughly equal to the Planck length, but containing a mass that could be anywhere from a few suns to billions of suns. It is the ultimate compact object, a quantum bounce frozen in time. This idea emerges most naturally from loop quantum gravity, a leading approach to unifying general relativity and quantum mechanics. In LQG, space itself is not smooth and continuous but is woven from tiny, finite loops. This granular structure prevents the infinite curvature of a singularity by providing a built-in repulsive force that becomes dominant at the Planck scale. The collapse doesn't end in a dead-end infinity. It experiences a quantum bounce. Think of it like compressing a spring. You can push down on it, but eventually the spring pushes back with equal and opposite force. In the case of gravitational collapse, the spring is spacetime itself, and the Planck star is the point of maximum compression before the bounce. However, this bounce isn't necessarily an explosive rebound that we could observe from the outside. From our perspective outside the black hole, the extreme gravitational time dilation means this bounce would appear to take an almost infinite amount of time. The Planck star is essentially a permanent, stable state at the center, forever hidden behind the event horizon. The existence of Planck stars would have monumental implications for resolving the most stubborn black hole paradoxes. The information paradox, for instance, could be neatly solved. If there is no singularity to destroy information, then the information about everything that fell into the black hole remains intact within the Planck star. Over the eons, as the black hole evaporates via Hawking radiation and the event horizon eventually shrinks away, this information could be released back into the universe. The firewall paradox might also be avoided. Without a true singularity, there's no need for a violent severing of quantum entanglements at the horizon to preserve information. The journey inward could remain smooth and uneventful all the way to the surface of the Planck star, preserving Einstein's equivalence principle. However, this elegant solution is not without its own set of profound new questions. If the Planck star is a real object, what is it made of? What is the actual state of matter at 10 to the 96 kilograms per cubic meter? This is so far beyond any state of matter we can create or even meaningfully describe that it remains pure speculation. Furthermore, the quantum bounce idea opens up a truly cosmic can of worms. Some models suggest that the bounce could be so powerful that it doesn't just stop the collapse but actually reverses it, transforming the entire black hole into a white hole. This would mean a black hole is not a permanent grave for matter, but a temporary tunnel, holding it for an unimaginably long time before spewing it back out. This idea connects the fate of individual black holes to the origin of our entire universe, with some theorists proposing that the Big Bang itself was the ultimate quantum bounce from a previous cosmos. The Planck star concept beautifully demonstrates how solving one mystery in physics often reveals a dozen more, taking us from the heart of a black hole to the very beginning of everything, all by daring to suggest that in the quantum world there are no dead ends, only new beginnings. Yet for all their immense gravitational power, black holes might hold the key to a force far more subtle and fundamental, the elusive quantum connection that could finally weave together the fabric of spacetime itself. This brings us to a mystery that operates on the smallest possible scales, where the bizarre rules of the quantum world meet the cosmic curvature of gravity head-on. It's the profound role of entanglement and how black holes, the universe's ultimate gravitational labs, are forcing us to see this spooky action at a distance, not as a mere particle phenomenon, but as the very glue that might hold the universe together. The quest to understand quantum gravity is the single greatest challenge in fundamental physics. We have two incredibly successful theories: general relativity, which masterfully describes the force of gravity and the large-scale structure of the cosmos, and quantum mechanics, which with stunning accuracy governs the world of atoms and particles. The problem is, they speak completely different languages and are fundamentally incompatible. General relativity paints a picture of a smooth, continuous, and deterministic universe where matter tells spacetime how to curve and curved spacetime tells matter how to move. Quantum mechanics, on the other hand, reveals a reality that is granular, probabilistic, and wildly unpredictable at the smallest scales. Put them together in an extreme environment like a black hole, and the equations produce nonsensical infinities. Clearly, a deeper theory is needed, one that can describe how gravity behaves when space and time themselves become granular at the tiny Planck scale. This is where black holes become more than just cosmic oddities. They transform into the perfect natural laboratories for testing ideas about quantum gravity. Their very nature creates a unique environment where both theories are pushed to their absolute limits. The immense gravity warps spacetime to an extreme, while the microscopic scale of the event horizon and the singularity demand a quantum description. Any theory that hopes to describe what truly happens at the heart of a black hole must successfully marry these two opposing worlds. It's a brutal, real-world test that filters out inadequate ideas. For instance, the information paradox isn't just a philosophical puzzle. It's a direct experimental constraint. A viable theory of quantum gravity must provide a mechanism for information to escape a black hole, or it can be immediately ruled out. The most promising thread in this grand unification seems to be quantum entanglement. Once dismissed by Einstein as spooky action at a distance, entanglement is now understood to be a pervasive feature of our quantum universe. When two particles become entangled, their properties are linked instantaneously, regardless of the distance separating them. Measure the spin of one, and you instantly know the spin of the other. For decades, this was seen as a curious property of particles, separate from the large-scale world of gravity. But groundbreaking work by physicists like Juan Maldacena and Leonard Susskind has turned that view on its head. Their ER equals EPR conjecture proposes a breathtaking equivalence. The wormholes predicted by Einstein's equations, known as Einstein-Rosen bridges, might be the geometric manifestation of quantum entanglement in the fabric of spacetime itself. Let's unpack that incredible idea. Imagine two black holes that are quantum entangled with each other. The ER equals EPR conjecture suggests that these two black holes wouldn't just be mysteriously linked, they would be physically connected by a wormhole, a tunnel through spacetime. This isn't just a nifty analogy, it's a proposed physical reality where the entanglement is the geometry. The greater the entanglement between two systems, the more connected their spacetime becomes. This provides a potential mechanism for solving the information paradox. If a particle falls into one black hole, its entangled partner outside could remain connected via this microscopic wormhole, providing a secret passageway through which information could, in principle, be preserved or even retrieved. This line of thinking has led to an even more radical proposal, that spacetime itself might not be the fundamental stage of the universe. Instead, what we perceive as the smooth, continuous fabric of space and time could be an emergent property, a holographic projection that arises from a vast, underlying network of quantum entanglement. In this view, the universe is like a cosmic quantum computer, and entanglement is the code that generates the illusion of geometry, distance, and gravity. The bonds between entangled particles are literally stitching spacetime together. Without entanglement, the very concept of space would fall apart. This means that the force of gravity might not be a fundamental force at all, but rather a side effect, a thermodynamic consequence of the universe's tendency to maximize entropy, much like how the pressure of a gas emerges from the collective motion of atoms. Black holes are the ideal place to test these profound ideas because they represent the limits of entanglement. When Hawking radiation is produced, the particles are created in entangled pairs. One falls in, the other escapes. As the black hole evaporates, this creates a problem. The escaping radiation particles must become entangled with each other to carry away the information, but they also need to remain entangled with the partners that fell in. This monogamy of entanglement problem is the root of the firewall paradox. Carefully studying the patterns of Hawking radiation, how these particles are correlated, could provide experimental data on how quantum gravity navigates this crisis. While we cannot yet perform these measurements on astrophysical black holes, physicists are creating analog black holes in labs using sound waves in superfluid helium or even in specially designed quantum computers. By studying how entanglement behaves in these simulated event horizons, we might catch a glimpse of the underlying quantum gravitational rules. The incredible promise is that by staring into the abyss, we are not just learning about black holes, we are deciphering the source code of the universe. The way black holes handle entanglement could be the Rosetta Stone that allows us to translate between the language of quantum particles and the language of spacetime geometry. Each gravitational wave signal from a black hole merger, each subtle detail in the shadow of an event horizon, and each lab-based simulation brings us closer to reading that code. The mystery of black hole entanglement is more than a puzzle. It's a portal offering us a chance to witness the birth of spacetime from the quantum void and finally understand the universe not as a place where things happen, but as a thing that itself is happening. Yet for all the mind-bending theories we've explored, from soft hair to wormholes, the most thrilling chapter in the saga of the information paradox is being written right now in the world's leading physics departments. This isn't just philosophical debate anymore. It's a hard-nosed mathematical attack on the problem, yielding the first concrete calculations that show, against all odds, how information might indeed find a way out. The epicenter of this revolution is a powerful new tool known as the island formula, and it's turning our view of the black hole interior completely upside down. To grasp this, we need to revisit the core of the problem. The paradox states that if you throw a book into a black hole, the information that made up that book seems irrevocably lost when the black hole evaporates, leaving behind only random thermal radiation. Quantum mechanics says this can't happen. The information must be preserved. For decades, the question was how. The island formula, emerging from the study of gravitational path integrals, provides a stunningly elegant and profoundly weird answer. It suggests that to calculate what an outside observer sees after the black hole has partially evaporated, you must include in your calculation not just the radiation that has escaped, but also a region inside the black hole itself. This region is called an island, a bubble of spacetime behind the event horizon that, through the bizarre rules of quantum mechanics, somehow contributes to the physics far outside. It's as if, to understand the data on your hard drive, your computer had to process information from a server that technically no longer exists. This approach relies on the concept of quantum extremal surfaces. These are not physical surfaces you can touch, but rather abstract boundaries defined by complex quantum calculations. They are the points where the rules of quantum entanglement and geometry meet in a very specific way. In the early life of a black hole, the relevant quantum extremal surface sits just behind the event horizon. But as the black hole evaporates and ages, a dramatic shift occurs. A new quantum extremal surface emerges, this one appearing far outside the horizon, and it becomes connected to that island region deep within the black hole's interior. This is the magic trick. The mathematics dictates that the information needed to describe the escaped radiation is no longer localized out there. It becomes inextricably linked to this island inside. From the perspective of the calculation, there is no longer a sharp distinction between the inside and the outside. The island becomes, in a quantum sense, part of the external system. So, what does this actually mean for our book? The information that defined it never actually makes a faster-than-light escape. Instead, as the black hole evaporates, the information becomes encoded in the correlations between the early, faint Hawking radiation and the later, more intense radiation. The island formula provides a precise way to calculate these correlations, and the result shows that the final state of the evaporated black hole is not random at all. It is a complex, scrambled, but perfectly deterministic transformation of the original material. If you could collect all the radiation, every last particle that flew off over billions of years, and you had a quantum computer powerful enough to perform the impossibly complex decryption, you could, in theory, reconstruct the entire book. The information was never truly lost. It was hidden in plain sight, woven into the tapestry of the radiation through quantum entanglement. This represents a monumental shift in the field. It's no longer about grand philosophical arguments. It's about doing the math and getting an answer that preserves quantum mechanics. The island paradigm suggests that the event horizon is not the impenetrable firewall or the information-destroying barrier we feared. Instead, it's a quantum-ambiguous boundary, and the interior of the black hole remains causally connected to the outside world in a way that defies classical intuition, ensuring that the universe always keeps a perfect, if deeply hidden, record of everything that has ever happened. This is the cutting edge where decades of paradox are finally giving way to a new and profoundly strange consensus, revealing a cosmos that is far more interconnected and faithful to its own quantum rules than we ever dared to imagine. Studying an object that, by its very nature, traps light and hides its secrets behind an absolute boundary is perhaps the ultimate exercise in cosmic detective work. How do you investigate a crime scene when the culprit has vanished without a trace, and the scene itself is locked inside an impenetrable vault? This is the daily challenge faced by astrophysicists, and overcoming it requires a blend of brilliant ingenuity, cutting-edge technology, and a deep understanding of the indirect ways a black hole announces its presence to the universe. The most obvious hurdle is the sheer darkness of the quarry. A solitary black hole drifting through the void is virtually undetectable. Without light or any other electromagnetic radiation coming from the object itself, our traditional tools of astronomy are rendered almost useless. We cannot image it directly, we cannot take its spectrum to determine its composition, and we cannot measure its light curve to understand its activity. It is a silent, invisible ghost in the cosmic graveyard. This forces astronomers to become masters of inference, learning to read the subtle, and sometimes not so subtle, gravitational whispers that a black hole imprints on its surroundings. It's like trying to deduce the shape, size, and speed of a ship by only studying the wake it leaves behind on a dark ocean. To peer into this darkness, we have had to fundamentally expand our concept of what a telescope can be. The Event Horizon Telescope's landmark image of the black hole in Messier 87 was a monumental triumph of this principle. It wasn't built as a single instrument, but as a coordinated network of radio telescopes spanning the entire globe, from the high deserts of Chile to the volcanoes of Hawaii and the frozen peaks of the South Pole. By synchronizing these observatories with atomic clocks and combining their data, scientists effectively created a virtual telescope the size of our planet. This colossal aperture was necessary to achieve the angular resolution required to resolve something as seemingly small as a black hole's shadow from 55 million light-years away. The data collected was so vast it couldn't be transmitted over the internet. It had to be physically shipped on hard drives to central processing centers where algorithms, developed over years, painstakingly reconstructed the image we all saw. This was not a simple photograph. It was a Herculean feat of international collaboration and computational power, all to capture the silhouette of nothingness. But light is only one messenger. The dawn of gravitational wave astronomy has opened an entirely new window on the universe, one that is perfectly suited to studying the most violent black hole interactions. Facilities like LIGO and Virgo don't look for light, they listen for the faint ripples in spacetime itself. They're incredibly sensitive instruments with lasers traveling down multi-kilometer long vacuum tubes can detect movements 10,000 times smaller than an atomic nucleus. When two black holes spiral into each other and merge, they don't produce any light, but they shake the fabric of the cosmos, sending out a telltale chirp that travels for billions of years. By the time this signal reaches us, it is almost impossibly faint, buried under a mountain of terrestrial noise from passing trucks, ocean waves, and even minuscule shifts in the ground. Isolating this cosmic whisper requires not just engineering perfection, but also sophisticated noise-canceling algorithms that can digitally subtract the predictable rumble of our world to reveal the faint song of the collision. This new sense allows us to hear the darkness, to sense black holes we could never hope to see, and to measure their masses and spins with precision. Perhaps the most common and productive method for finding black holes is to watch how they influence their stellar neighbors. This is how we discovered the first stellar mass black hole candidate, Cygnus X1. Astronomers observed a massive blue star apparently orbiting around nothing. By carefully tracking the star's motion, they could calculate the mass of its invisible companion. The result was an object far too heavy to be a neutron star, leaving a black hole as the only plausible explanation. Similarly, the presence of the supermassive black hole at the center of our own galaxy, Sagittarius, a star, was confirmed by meticulously tracking the orbits of stars near the galactic core for over 2 decades. These stars were seen whipping around an invisible point at speeds exceeding 5,000 kilometers per second, following elliptical orbits that allowed scientists to pinpoint the mass and location of the unseen gravitational anchor with astonishing accuracy. We know it's there because we can see the stars dancing around it. Finally, we learn about black holes by witnessing their most voracious phases. When a black hole actively feeds, pulling gas from a companion star or a surrounding accretion disk, the material doesn't go quietly. As it spirals inward, it is compressed and heated to millions of degrees, causing it to glow intensely across the electromagnetic spectrum, particularly in high-energy X-rays. Space telescopes like Chandra and New Star are our eyes for this violent light. By analyzing the intensity and spectrum of this radiation, astronomers can infer the black hole's mass, its spin rate, and the properties of its accretion disk. They can even see the light from material just milliseconds from the event horizon, stretched to longer wavelengths by the extreme gravitational redshift. In these fleeting, brilliant moments of destruction, the black hole is momentarily illuminated by the dying scream of the matter it consumes, offering us a precious, indirect glimpse into the physics of the abyss. Each of these methods, from building an Earth-sized telescope to listening for space-time ripples to charting the paths of captive stars, is a testament to human creativity, proving that even the universe's most perfect hiding places cannot completely conceal their secrets from a determined and curious mind. But what if the very rules of gravity we've been relying on are incomplete? For over a century, Einstein's general relativity has reigned supreme, its predictions about black holes passing every test. Yet, the theory's glaring incompatibility with quantum mechanics and its inability to explain dark energy suggest it might not be the final word. This leads us to a thrilling frontier of theoretical physics, the possibility that black holes could look and behave utterly differently in alternative theories of gravity, serving as cosmic laboratories to test the laws of the universe themselves. In the world of string theory, black holes are not point-like singularities but complex, vibrating entities known as fuzzballs. This theory proposes that the fundamental building blocks of reality are not particles but tiny, one-dimensional strings. When applied to black holes, the idea of a sharp event horizon and a vacuum interior vanishes. Instead, the entire region inside what we would call the event horizon is filled with a giant, tangled ball of strings, a fuzzball. This structure has no singularity and no smooth, empty space behind the horizon. It's a dense, quantum mechanical object that extends right to its surface. The profound implication is that there is no information paradox because there is no point of no return. An astronaut falling into a fuzzball wouldn't experience a smooth ride into nothingness. They would collide with this stringy surface almost immediately. The event horizon, in this view, is an illusion, a transition zone into a vastly different kind of object. While directly observing a fuzzball's stringy nature is beyond our reach, string theory makes other predictions, such as the existence of a vast landscape of possible universes and unique types of lower-dimensional black holes called black strings, which could leave distinct imprints in the fabric of space-time. Meanwhile, loop quantum gravity takes a different approach, suggesting that space itself is not smooth and continuous but woven from tiny, discrete loops. This granularity at the Planck scale provides a natural repulsive force that halts the complete collapse of matter into a singularity. The result is not a fuzzball, but a Planck star, a supremely dense remnant at the black hole's core, forever hidden behind a horizon that only appears classical from the outside. As the black hole evaporates via Hawking radiation, a fascinating transition occurs. The event horizon shrinks, and eventually, the quantum gravitational interior containing the Planck star could be exposed. The moment of a black hole's final evaporation might not be a silent whisper but a powerful explosion, a last gasp revealing the quantum structure of spacetime. This could provide a spectacular observational signature, a very specific high-energy flash of gamma rays that would be the smoking gun for loop quantum gravity, a final firework show signaling the death of a black hole and the birth of a new physics. Other theories propose more radical modifications. Massive gravity, for instance, suggests that the graviton, the hypothetical particle carrying the gravitational force, has a tiny mass. In Einstein's theory, gravitons are massless, which is why gravity has an infinite range. If they have even a minuscule mass, the nature of gravity changes at very large distances. This could eliminate the need for dark energy to explain the universe's acceleration, as the modified gravitational field itself would cause the expansion to speed up. For black holes, massive gravity predicts that their gravitational fields would weaken differently with distance compared to Einstein's predictions. This could lead to hairy black holes with additional fields surrounding them, or even black holes that are not perfectly black, capable of shedding their hair in a detectable way. Observations of the orbits of stars around our galaxy's central black hole, or the precise shape of the shadow cast by M87's black hole, could reveal subtle deviations that point toward a graviton with mass. The challenge and the excitement lie in finding ways to test these ideas. The Event Horizon Telescope is not just taking pictures, it's a precision instrument for measuring the exact size and shape of a black hole's shadow. A shadow that is too small, too large, or not circular enough could immediately rule out Einstein's theory in its purest form and point toward an alternative. Similarly, gravitational wave observatories like LIGO and Virgo are listening for the specific chirp of colliding black holes. The precise pattern of these waves encodes information about the nature of the objects that created them. A deviation from the waveform predicted by general relativity, perhaps an echo from the quantum structure just outside a fuzzball surface or a hint of extra dimensions from string theory, would send shockwaves through the physics community. We are no longer just confirming Einstein's genius. We are actively probing for cracks in his masterpiece, searching for the subtle cosmic fingerprints that will guide us to the next deeper theory of everything. Beyond the complex equations and the cutting-edge observations, the study of black holes forces us to confront questions that have haunted philosophers for millennia, challenging the very framework through which we understand reality itself. These aren't just scientific puzzles, they are profound existential riddles that probe the limits of human knowledge and our place in a cosmos that seems increasingly alien. If information can truly be lost within a black hole, what does that say about the universe's fundamental predictability? The principle of determinism, the idea that the future is entirely dictated by the past, is a cornerstone of classical physics. If you know the precise state of every particle in the universe, you should, in theory, be able to calculate everything that will ever happen. But the black hole information paradox throws a wrench into this clockwork universe. The potential destruction of information suggests that the cosmos might contain irreversible erasers, points of no return not just in space but in causality itself. This introduces an element of fundamental randomness or unpredictability at the gravitational scale, a notion that would make the universe inherently unknowable in its entirety. We are left to wonder if some events, what happens beyond an event horizon, are simply beyond any possible reconstruction, creating permanent gaps in the cosmic story that no amount of scientific advancement could ever fill. This directly challenges our anthropocentric tendency to believe the universe is structured for our comprehension. For centuries, we've operated under the assumption that nature is ultimately rational and explicable. But black holes stand as monumental counterexamples. Their interiors are causally disconnected from our universe. No signal, no piece of data, no story can ever escape. They represent absolute epistemic boundaries, realms that are, by their very nature, inaccessible to observation or experiment. This forces a humbling realization: the universe might not be designed for our understanding. It may contain permanent mysteries, facts about reality that are true but forever unknowable to us. This isn't a temporary limitation of our technology. It's a fundamental feature of the cosmos, baked into the laws of physics. Accepting this means embracing a universe that is vast not just in space and time, but in its capacity for secrets, forever holding some truths just beyond our grasp. The very nature of time is also warped beyond recognition within a black hole's grasp. From the perspective of an outside observer, time grinds to a halt at the event horizon. An object falling in appears to slow down, redden, and fade, frozen forever on the brink. Yet, for the individual making the plunge, their clock ticks forward normally until they meet their fate at the singularity. This isn't an illusion. Both perspectives are equally valid within their own reference frames. There is no single universal now. This radical subjectivity of time, a direct prediction of general relativity, is demonstrated in its most extreme form by black holes. They force us to abandon the comforting notion of a single, flowing timeline for the universe and accept that time is a personal, local experience, woven into the fabric of space-time and stretched to its breaking point by gravity. Our intuitive sense of time as a river flowing in one direction completely shatters against the immense gravity of a black hole. Ultimately, black holes serve as the ultimate cosmic sphinx, presenting us with riddles that touch on the nature of existence itself. They are regions where the universe folds in on itself, where the rules of reality are written in a language we have not yet deciphered. Do they represent the ultimate end, the final victory of chaos and entropy over structure and information? Or are they portals, transformers, or even cradles for new universes, as some theories suggest? The ethical dimension even emerges when we consider far future civilizations. If harnessing the energy of a black hole through something like the Penrose process becomes possible, it raises questions about our responsibility toward these cosmic entities. Would tampering with them, potentially altering their evolution or even hastening their evaporation, have unforeseen consequences on the fabric of space-time or the future of the galaxy? They are not just objects out there, they are mirrors reflecting our deepest questions about knowledge, reality, and our own fleeting presence in a universe whose deepest truths may forever lie in the heart of darkness. And yet, even with all these profound mysteries swirling around us, from the fate of information to the nature of space-time itself, the most exhilarating thought is this: we are not at the end of this story. In many ways, the golden age of black hole research is just beginning, poised on the verge of a revolution powered by a new generation of telescopes and observatories that will peer deeper into the darkness than ever before. We are building the tools to move from inference and theory to direct observation and confirmation, to finally hear the whispers and see the shadows that will answer questions we've been asking for half a century. One of the most anticipated missions is the Laser Interferometer Space Antenna, or LISA. While ground-based observatories like LIGO and Virgo have opened our ears to the high-frequency chirps of stellar mass black holes colliding, they are deaf to the lower, deeper songs of the cosmos. LISA will be a gravitational wave observatory in space, consisting of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. This vast scale will allow it to detect the low-frequency rumble of the universe's most massive events, the mergers of supermassive black holes. Imagine listening to the sound of two black holes, each weighing billions of suns, spiraling together in the core of a distant galaxy. This is not just about detecting more events, it's about hearing an entirely new part of the gravitational wave spectrum. LISA could allow us to map the growth of these giants across cosmic time, tracing how galaxies merged and evolved through the collisions of their dark hearts. It might even detect the faint background hum from all the binary black holes in the universe, a cosmic choir singing since the dawn of time. But our eyes are also getting sharper. The next generation of extremely large telescopes, like the giant Magellan telescope and the 30-meter telescope, will have mirrors so vast and adaptive optics so precise that they will be able to track the motions of individual stars orbiting ever closer to the event horizon of Sagittarius, a star, the supermassive black hole at our galaxy's center. This isn't just about confirming its mass, it's about testing general relativity in an extreme environment with unparalleled precision. Will the star's orbits perfectly follow the paths predicted by Einstein, or will we see tiny, telling deviations that hint at new physics? These telescopes will also be powerful enough to watch the inner regions of accretion disks around distant black holes in stunning detail, potentially allowing us to see the effects of frame dragging and magnetic fields directly, and to witness the launching points of those relativistic jets in real time. And let's not forget the Event Horizon Telescope is not a static project. The iconic image of M87 was just the beginning. By adding new telescopes to the array, particularly in space, the EHD collaboration aims to create ultra-high-resolution movies of black holes. Instead of a single snapshot, we could watch the flow of material around the event horizon over days, weeks, and months, seeing how the bright, hot spots in the accretion disk evolve and change. This would transform a static picture into a dynamic portrait, revealing the turbulent weather patterns just outside the point of no return and giving us a direct view of how black holes consume their meals. The questions these new tools are designed to answer are as grand as the instruments themselves. We want to know definitively if general relativity holds supreme at the event horizon, or if we need to invoke quantum gravity or modified theories to explain what we see. We want to solve the information paradox once and for all, to understand if black holes are the ultimate vaults or the ultimate shredders. We want to pin down the origin of supermassive black holes. Did they grow from the corpses of the first stars, or were they born large from direct collapse in the early universe? And perhaps most profoundly, we want to understand the true connection between black holes and the large-scale structure of the cosmos. Is dark energy somehow locked within them? Do they play an active role in shaping the evolution of galaxies, or are they simply passive byproducts? The next few decades promise to be a period of unprecedented discovery, where the mysteries that have captivated and confounded us for generations may finally yield their secrets. We are no longer just staring at the darkness. We are building the lanterns that will illuminate it, ready to step forward into a new understanding of the most extreme and enigmatic objects in creation. The future of black hole research is not about closing the book on these cosmic monsters, but about learning how to read the incredible story they have been trying to tell us since the beginning of time. From the enigma of the information paradox to the terrifying possibility of firewalls, from the quest to understand singularities to the hunt for wormholes and white holes, these 30 mysteries are far more than a simple list of cosmic curiosities. They represent the absolute frontier of human understanding, the very edges of our map of reality where the known rules of physics fray and dissolve into pure potential. Each unanswered question is a doorway, inviting us to step beyond the comfortable confines of Einstein and quantum mechanics and into a new, deeper theory of everything. Whether it's the puzzle of how supermassive black holes grew so large so quickly, the search for the missing intermediate mass link, or the profound implications of the holographic principle, these are not isolated problems. They are interconnected threads in a grand cosmic tapestry, each one pulling on the others, suggesting that a solution to one might unravel the entire beautiful, complicated knot. This journey through the unknown highlights a breathtaking truth. Black holes are not merely destructive ends. They are catalysts for creation, engines that power galaxies, potential seeds for new universes, and the most rigorous laboratories nature has ever provided for testing our most fundamental ideas about space, time, and information. They force us to question the nature of reality itself, to wonder if our universe is a hologram, if entanglement is the fabric of space-time, and if the past is truly set in stone. The ongoing detective work, from the Earth-sized ambition of the Event Horizon Telescope to the delicate listening of LIGO and the forthcoming promise of LISA, is a testament to our species' insatiable curiosity. We are building ever more sophisticated tools to listen to the whispers of gravity and stare directly into the abyss, not in fear but with a relentless desire to understand. So, as we conclude this exploration of the universe's greatest puzzles, remember that the story of black holes is still being written. Every new observation, every theoretical breakthrough, and even every stubborn paradox brings us closer to a revolution in physics that will likely redefine our place in the cosmos. The mysteries that seem so impenetrable today are the very questions that will guide the next generation of scientists and dreamers. Stay curious, stay awe-filled, and keep looking up at the dark spaces between the stars. For hidden within that darkness are not just monsters of gravity, but the keys to unlocking the deepest secrets of existence, waiting for a curious mind to finally turn the lock. What's truly incredible is that you don't need a billion-dollar telescope or a PhD in theoretical physics to become a part of this grand exploration. The quest to understand black holes has moved into the realm of citizen science, where anyone with curiosity and an internet connection can contribute to real discoveries. Projects like Zooniverse host initiatives where you can actually help astronomers sift through mountains of data. You might be tasked with scanning through radio telescope images to identify the telltale jets of supermassive black holes, or classifying the light curves of distant quasars to see how their brightness fluctuates over time. The human eye and brain are still remarkably good at pattern recognition, often spotting anomalies that computer algorithms might miss. Every classification made by a volunteer adds another piece to the puzzle, helping professional scientists map the distribution and behavior of these enigmatic objects across the cosmos. If you're feeling inspired to dive even deeper, a wealth of resources is available to fuel your curiosity. Free online courses from platforms like Coursera and edX offer university-level classes in astrophysics and cosmology, taught by leading experts from institutions around the world. You can find countless lectures, documentaries, and podcasts that break down these complex concepts into engaging and understandable stories. For those who love to read, books by authors like Neil deGrasse Tyson, Brian Greene, and the late, great Stephen Hawking himself provide breathtaking tours of the universe's greatest mysteries, written for everyone from the complete novice to the dedicated amateur. Following leading research organizations like NASA, the European Space Agency, and the Event Horizon Telescope, collaboration on social media will keep you on the cutting edge, giving you a front-row seat to new images and announcements as they happen. This journey into the unknown is fueled by wonder, and that wonder is a deeply personal experience. As we've traveled through these 30 mysteries, from the fate of information to the nature of singularities, which one captured your imagination the most? Does the sheer destructive power of spaghettification both terrify and fascinate you? Are you captivated by the elegant, universe-spanning connection proposed by ER equals EPR? Or does the mind-bending possibility of white holes and new universes spark your sense of cosmic possibility? Share your thoughts in the comments below. Let's start a conversation about which of these profound puzzles you find most compelling. Your perspective, your questions, and your passion are what keep the spirit of discovery alive. By learning, questioning, and even participating, You become part of a timeless human endeavor to look up at the dark, silent sky and dare to